As we start assembling, I'd like to welcome you to our third version of our now, I guess it's now a tradition after 3 times, of day-to-day at Carleton. We have a very full day, and I welcome you. So some people are a little bit delayed because of if you were here last year, there was a parking lot. Now there's a brand new building going up, so you have to look around a little bit. But that's the way, as someone mentioned to me, that's the way you get your 10,000 steps a day. It's trying to get here from somewhere else. So to kick off the day, it's my pleasure to introduce our president, Roseann Runte, President and Vice-Chancellor of Carleton, who will give some opening remarks. Roseann?
Thank you very much, John, and thank you all for getting up early on this glorious day. And thank everyone who has submitted a poster or doing a workshop. You're all wonderful, but especially John for organizing this. Let's say thank you to him. A few years ago, I was president of another university in Toronto, Victoria University, and it was special because my predecessor was North Fry, the great literary critic, and it was like living with a legend. He was very elderly, and he would go around and, whatever he say, people were writing it down because it was like, a great word of wisdom would come from his lips. I've been trying to channel that ever since. It hasn't worked. Anyway, one day at lunchtime, he was sitting in the senior common room, and he had the newspaper in front of him. And there were some faculty on the little coffee table, and they were doing a crossword puzzle. And they were stuck. And so at one point, they said, Nori, short for North Fry, Nori, do you know a 4-letter word for bitter vetch? And there's silence behind the newspaper, and then a little rustling of the paper, and it comes down, and he says, I don't know any 4-letter words. He only knew longer words. And I'm thinking to myself, data, 4 letters, and he didn't know about it. The same week that he said that, I had the opportunity to walk over to St. Mike's and visit Marshall McLuhan. And he said, we need all the information possible to make good decisions. And computing is going to do that. It's going to get better and better, and we're going to have more and more information, and we'll be able to really be wise and make truly good decisions. And so, I go back to my office and I think to myself, wow, we'll make 7-letter words and great decisions, and computers will be great and save the day. And I really didn't quite imagine the fact that it would be so great that we'd have so much information, it would be even harder to make a decision than it was before we had sufficient information. And the fact that big data it's like a gold mine. We could do anything with it, but the question is how? And how can we organize it so that we have enough time to do something with it? Because we seem to have less time the older we get, and the less time, the more things that we have to do with our lives. So I was really thrilled when a number of years ago at Carleton, faculty said, yes, big data is a subject we need to study. And we need to study it in a different way from everyone else. Not just study the data, the machines that make it, and how it's processed, but how do we use it in every field? How does it affect your life if you are a poet? How does it affect your life if you pay taxes, if you drive a car? How can you use big data to make the right decisions? Because now we have a resource and we need to harness it. So I am absolutely delighted at the work of our faculty, which has come together so many departments to struggle with this issue. How do you use it to make good policy? How do you use it to make better government? We all could use some of every one of the above. So I thank you for being part of this extraordinary initiative, part of the future, part of a world where words don't have to end with 7 letters. They can have 25 letters, and they'll still make sense. So thank you. I'd ask you all, especially not the ones with cups in your hands, to pat yourselves on the shoulder and say, thank you for getting up early and doing this. It was the right thing to do, and I applaud you. Thank you.
Okay, thank you, President Runte. My name is Jim Green. I'm the Interim Director of the Institute for Data Science. I'll just have a few brief announcements this morning. So the Institute officially opened its doors on April 1st of 2015, and we've accomplished a lot in just 1 year. While the Institute was multidisciplinary from its inception, we continue to grow and diversify. We're happy to announce that the School of Journalism and Communication has recently joined the Collaborative Master's Program in Data Science, now offering a Master of Arts in Communication with a specialization in data science. This past year, we rapidly hit our enrollment capacity of 40 new graduate students in the program and expect to repeat this again in 2016. During this academic year, we have held over 10 seminars and technical workshops here at Carleton University. These events are completely free and open to everyone and have been very well attended. I've learned I have to get there early if I want one of the free cookies. We've hosted 7 seminars with distinguished speakers from the National Research Council, Open Government and the Treasury Board Secretariat, the University of British Columbia, IBM, and Carleton University. These seminars have often led to lively and constructive discussions among the multidisciplinary audience and the expert speakers. We've hosted 3 technical hands-on workshops led by IBM and Microsoft evangelists. In these workshops, participants are able to test drive world-class data analytics tools on their laptops, gaining real exposure to emerging technologies. We've also recently kicked off a series of Big Data University meetups in collaboration with IBM and look forward to continuing these throughout the summer. These meetups are open to everyone and cover important nuts and bolts data science skills through hands-on workshops. In fact, Big Data University is represented here at a booth, and we encourage you to stop by today. With all that we have accomplished over the last year, we anticipate great things to come. We're looking forward to growing the Institute through industry and academic collaborations and partnerships with new faculty, student, and industrial memberships. We encourage anyone who is interested in collaborating with the Institute to contact us. We've already had multiple requests from government and industry seeking advice on how to grow and develop their own in-house data science expertise, bringing with them exciting opportunities to initiate new research and development collaborations with our members. The Institute for Data Science currently has 53 participating faculty members from across the university, and I'd like to take this opportunity to invite any faculty in attendance today to consider joining the Institute if you've not already done so. We've recently had new members join from the Department of Health Sciences and the School of Public Policy and Administration, some of whom will be speaking to you today. In fact, we will be holding our first annual retreat for members of the Institute in 3 weeks' time on April 19th. This will be an opportunity to get to know your colleagues within the Institute, to share ideas, and to launch new collaborations. As I reach the midpoint in my tenure as Interim Director of the Institute, I'd like to thank and acknowledge John Apsimon and Catherine Elliott for the enormous support that they provide to the Institute. They are largely responsible for today's event, and with over 300 registrants, they're clearly doing something good. I have just a few more announcements before I invite Rafik Goubran, Dean of the Faculty of Engineering and Design, to take the podium and moderate this morning's session. The presentations today are being live streamed in the Atrium and also on our website. All presentations will be available on our website in the coming weeks. We have 7 booths set up in the Atrium for you to visit today, including representatives from Big Data University, Hacking Health, IBM, the Faculty of Science, the Faculty of Engineering and Design, Carleton Research Computing Services, MyTax, Interset, and the McCodrum Library with their Dataverse program. There is boardroom space that will be available to anyone who would like to use it for interviews or meetings, etc., throughout the day. Please see the registration desk for more information. We have 19 graduate students participating in today's poster competition in academic disciplines ranging from biology to engineering, political science to computer science, economics to architecture. These students represent the breadth of data science and analytics research taking place at Carleton University. Please feel free to browse their posters and ask them really tough questions. Lastly, we thank our sponsors for today's event, IBM, Invest Ottawa, Canary, Interset, Cisco, and the Canadian Advanced Technology Alliance. I hope everyone enjoys Day-to-Day 3.0. Thank you. Dean Goubran.
Good morning. For the next 20 minutes or 25 minutes, I'll talk to you a bit about data, big data, but one aspect of big data, which is the aspect of sensors and then real-time data analytics. So first of all, let's see what happened in the technology in the past few years, and then we'll talk about sensors a bit more. So technology evolution. So first of all, in terms of being able to put tiny components into chips, this has grown a lot over the past few years. So for example, chips like the Intel Core i7 that you hear about in your computers and laptop and so on, has got 1.4 billion transistors, meaning that it has 1.4 billion tiny components inside it that make it do whatever it does. An Apple 8X chip, for example, has got 3 billion transistors inside it, which makes it extremely complex and being able to do a lot of things. So that's the first one. So now chips have got a lot of stuff inside them and they can do a lot of things. The ability to incorporate micro-mechanical systems. So right now inside those chips, you can incorporate micro-mechanical components that help them be able to do things we never thought of in the past, like work as an accelerometer to measure acceleration, speed, distance, and so on, gyroscopes, miniaturized motors, and so on. Then those chips as well have got wireless connectivity, meaning that one of those tiny chips have got a lot of computational power to do a lot of things. At the same time, it has mechanical components that help it do things that we never thought of before, but also that chip has got wireless capabilities so that it can connect with other chips, whether we're talking about the standard channels like Wi-Fi or 4G. We have new technologies that are coming up, such that as, for example, Bluetooth low energy or near-field communications that allow different type of communications to happen. So these advances led to the introduction of a new generation of chips with very low energy consumption, very high processing power, and also wireless connectivity available there. So as a result of this, there are many, many sensors that became available. So what are sensors? Sensors measure input from the surroundings. So you can have a sensor that measures light, measures heat, measures humidity. Some sensors now, like polymer sensors, can measure smell, taste, acceleration, pressure, electric signal, you name it. These sensors can measure so many things in the surroundings. And then with the processing power that we have, we can make a lot out of those. So you can measure, as I said, vibration, you can measure taste, smell, anything else. So what are the characteristics of those sensors? Well, they are usually extremely small in size. So we're talking about a sensor that measures less than 1 millimeter square, for example. Extremely low cost. So if you go and buy those sensors, especially in quantities, you may pay a few cents per sensor. Minimal power consumption. So some of those sensors with a battery, it can last for maybe 2-3 years. So again, minimal power consumption and also wireless connectivity. So those sensors are used now throughout the world, everywhere. So I bet you that by the time you came in this morning, you probably saw hundreds of those sensors. When you touch your phone, there's a sensor there. Clock has got one, dishwasher, fridge, car, everything around you is full of those sensors. So they're being used for healthcare, for security, home appliance, manufacturing, cars, airplanes, smart homes. So now, give you examples of sensors. So you have pressure sensors that can measure any pressure applied on those sensors. You have microphone arrays. So you have very tiny microphone arrays that could even go into hearing aids. So you have hearing aids that have got now several microphones, and those microphones can do a lot of things. Like, for example, when you're in a very noisy environment, let's say the poster session, and lots of people are speaking, then the microphone array can actually focus on the person in front of you. So for those who have hearing impairments, they would not hear anything from the background, they'll hear only what's in the front. If they go outside, then the back opens as well. So you have now tiny, tiny sensors. In the past, microphone arrays used to be something that requires a crazy supercomputer to run or something like that. Right now, the microphone arrays, as I said, can be incorporated into a hearing aid. Smell and taste sensors, accelerometers, infrared sensors, temperature and humidity, light and color sensor, proximity sensors. So now with all of those sensors deployed everywhere, we have a new situation nowadays where, if you remember, in the past, we were not able to make the right decision sometimes because we did not have enough data to give us an idea of what's going on. Now the same thing is happening, but it's because we have too much data and we're overwhelmed by data, so we're not able to make the right decisions because we cannot see the right information into that data. So the whole area of big data, data science, and data analytics, essentially in a couple of words, is how to extract useful information from the massive amount of data that exists around us. And now in this talk, I'll focus more on data that's generated by sensors that we need to process on a real-time basis. So I'll give you here some examples of applications. So for example, pressure sensors. So this is material like texture that has got embedded sensors there where you can measure the pressure on every part of that texture or that material. So what do we use it for? Well, wearable sensors that can measure your heart rate, your breathing rate, and many other things. You can put them on the floor to measure, to do gait analysis for security, you can for occupancy, and so on. You can put them under the mattress of a bed, and then if somebody sleeps on the bed, you can detect bed occupancy, you can detect breathing, things like sleep apnea, for example, weight changes during the night. So you could see actually the weight of a person during the night moving from one place to another to detect some things like fluid retention and congestive heart failure. You can put them, as I said, on the floors to perform gait analysis, biometrics, security, and so on. Now, microphone arrays, you can have them in teleconference systems. You can have them in hearing aids. You can have them in many devices. Now, several of the phones have got multiple microphones and can do beamforming. You can have them for tracking people in noisy places. So you can do things like speech detection. Speech detection is automated speech. So you say something, and then the system understands what it is. We're all familiar with that. Speaker recognition, it's not recognizing what you say, but it's more recognizing who you are. So if you train the system, then if we train the system to recognize John, so whenever John speaks, the system will say, this is John who's speaking. You can actually train the system, and researchers at Carleton have been involved in all of those areas. So native language recognition. So you can recognize actually the native language or the native tongue of the person who's speaking. Like if somebody's got a certain ethnic origin, so then you can recognize where they come from. So this is used for homeland security and for other purposes as well, for specialized speech recognition. You can have audio classification, security, medical applications. You can check coughing, snoring, and so on using the microphone arrays. Electronic noses, again, it's an array of sensors that recognizes odors. So it can be used for many, many applications. You probably have seen some electronic noses, big ones, the ones you see at the airport when they swipe your laptop and then feed it into the big machine there, the Smith detection machine, to detect whether there's any plastic explosives or whatnot. Now, some of those sensors are so tiny that many smartphone manufacturers have announced that these sensors will be incorporated into the phones. So think about applications. Application from maybe using all phones to detect explosives sometimes. That's a possibility. But also applications like in terms of cooking, in terms of measuring the alcohol level in the breath, measuring tasting wine. and so on. So you'll find a lot more applications that are happening. Some of them deal maybe with narcotic detection, explosive detection, but also lots of other applications from hygiene to cooking to wine selection. Now, other sensors are accelerometers and gyroscopes. So those are embedded into our phones so that, for example, in some of the phones, if you do a mistake, you knock the phone and then it can undo what you've done. This is an accelerometer that detects that. You can have lots of applications that measure your gait or your steps to see how much calories have you burned and so on. This is done due to the accelerometers that are embedded into those various devices and smart phones. Now, other applications are coming up as well, like, for example, now with a video camera, looking at somebody, you can do elaborate signal processing and image processing to extract a lot of information from the video that you're collecting. So in fact, there are apps right now that you can use whereby if I take the phone and let's say focus on Jim there and take some video of Jim, or even if I get a video that was taken from Jim 20 years ago, I can do an analysis of that video and then look at the tiny color changes that are happening in the face. So if I take that individual there and then look at the tiny color changes that are happening in the face, I could see those signals going up and down. So this is color changes in the face that will tell me a lot of things. So by looking at this, I can tell you what is the heart rate of that individual. So I can look at a movie that was done 20 years ago and then do some analysis and tell you what was the heart rate of every individual there in the movie. Now, how is that used? It's used to measure anxiety, to do remote check of various things. Not just that. If I look at it in detail and I look at that shape of the signal, I can extract a lot of information about how the heart is working and detecting some heart disease. In fact, if I do the face and the hand, so I'm trying to detect the heart rate from the face, I'm trying to detect the heart rate from the hand, and then by looking at the different timing between the two, I can tell you any variation in blood pressure. So you can do even some measurements of variation in blood pressure by remotely using a camera. So all of those sensors that are available around us are helping us do a lot of things. Other very tiny sensors that are available right now, you can see it here. This is a camera that's called the Seek camera that sticks here on a smartphone. So this is a thermal camera. So it doesn't measure the optical, what you see, but it actually measures the temperature that you see in front of you. So for example, if you use it and look at pipelines, you can see if there is an issue with the pipeline, you can look at your hand and then find issues with your hand with respect to inflammation, with respect to pain, and so on. You can use it when quadcopters, for example, and drones in order to see what's happening in a certain area and see, do night vision and check our infrastructure. So if we go back here, you can see applications related to, for example, security, safety, security, infrastructure protection, monitoring people at night in terms of intrusions and so on. But you can use it for medical applications as well. Like actually one of the students here did a few papers on looking at your face with a thermal camera and then looking at temperature variations around the nose. And from there, you can say how much breathing is the person doing. So that's used for things like detecting sleep apnea and whatnot. So this is another example of some sensors that are available nowadays that can help us in our daily living. But also all of those sensors are generating so much data, where actually data analytics is more about how to analyze this data and extract useful information out of it. So now smartphones give us a tremendous potential because smartphones have got microphones. Many of them now have got multiple microphones, have got multiple cameras, light sensors, accelerometer, gyroscope, barometer, touch ID, humidity sensors, touch sensors, and in the future, you're going to have electronic noses as well, and maybe more and more sensors coming in. The phone itself, as I said at the beginning, has got chips that have got a lot of power in that chip. So you can do a lot of processing to extract useful information out of this data. Now, the phone has got communications as well. So it helps you send that data everywhere. It has very nice user interfaces. So smartphones can be used to monitoring individual when it comes to biomedical engineering. They can be done to do things like, for example, determine traffic in a certain road by seeing each phone, how does it move. So there are applications now that use all of the phones of everybody to get more information or more data and then more information about what's happening in general. So smartphones not just can use their internal sensors, but smartphones can also acquire data from external sensors. So if you make an environment here smart by inserting sensors in various places, then the smartphone can extract data from those sensors, do some analysis in terms of data analytics, and send the data along with its own context, its own internal data, and be able to do it properly. So as I said then, so the main challenge that we will face in the future is how to extract useful information from the vast amount of data that we have or will be collecting using all of those sensors deployed everywhere. This information could be clinical information, if we're talking about health. It could be safety and security information, if we're talking about infrastructure protection. It could be information from an engine of a plane or from the car or anything else. So the area of data analytics is now vital to all disciplines, going from computer science to engineering to arts to social science to politics to everywhere now you have this data and we have to deal with it. In fact, data analytics have been identified by the Global Engineering Deans Council as the main trend in engineering for the next decade. Now, we are relying on sensors on many aspects of our life. This presents a really great opportunity, but also it poses some risks and vulnerabilities. Because if you have all of those sensors in your home that measure everything in your home and cameras and everywhere else, we think that this will help us, make our life simpler and more efficient and so on. But also intruders can come in and use that data and affect you. So the more data available about yourself and everything else, it could create some vulnerabilities that we have to worry about and deal with as it goes. So these sensors that I talked about, coupled with advanced data analytics, is essentially a technological revolution that we're having right now. New disciplines are coming up, like the Internet of Things and others. Novel solutions, novel cost structures are now challenging the conventional solutions that we're familiar with, and we have to think outside the box. So now let me talk about another aspects related to data analytics. So let me give you examples to show you that data analytics is not in one area, it's all over. But I want to emphasize what is the difference between real-time data analytics and non-real-time data analytics. If you're having data coming in about, let's say, genes and impact on various disease and epidemiology and so on, so all of this data is coming in from people over the years, so you have a huge amount of data. Then you analyze this data to find the relationship between some genes and some disease and try to look at it from that perspective. Then that's called non-real-time data analytics, or big data analysis. So if it takes you a week to analyze that data, that's perfectly fine. It took years to collect that data. So if it takes a week, it's no big deal. Now, if you're in an operating room and you have sensors on the patient now being operated on, and you're looking at the heart rate, at the blood pressure, everything else, oxygenation level, and so on, and then you have to make decisions, you cannot afford to wait for too long. This is, again, a data analytics problem where timing is of essence. So this is where real time is. I'll give you another extreme case of real time. You would think of data analytics, yes, I'm collecting data, it sits in a computer somewhere and somebody's analyzing it. But that's not all data analytics. I'll give you another example. When you drove to Carleton this morning, whether you were driving or you're in a bus or a cab or whatever, I'm sure somebody pressed the brake at some point in time to stop at a stop sign or traffic light. What happens in the car when you press the brakes? Well, in the past, it used to be a mechanical system that goes and stops the car or activates the brake. But right now, it's far more complex. Right now, when you press the brake, you're telling a computer, I want to stop the car. Then the computer there looks at the data around you. It looks at what is the speed of the car? What is the direction of the car? What is the direction of your steering wheel? What are the conditions of the road based on some information? What is the engine RPM? What is how much are you pressing? How fast and then it makes a decision and decides what is the best way of stopping the car right now. This is a data analytics problem. But if it takes 10 seconds to give you the exact right solution, well, that's too late. Okay? So in this type of data analytics, it's real-time data analytics where time is of essence, because if you give me the optimal solution in 10 seconds, I don't need it. An accident would have happened already. But I need it instantaneously in a fraction of a second or a few milliseconds. I need the response, even if it's not the optimal response. But I need the response based on the information or the data that I have, based on everything that I have, I need to make a decision within a split second, and then I make that decision. So that's where I guess the researchers in data analytics are usually in two groups. One is more the big data analytics, where time is not of essence. Obviously, you want to have the solution in a week instead of a month, but there's a big difference between that and between the hard real-time constraint, where if you do not get your proper answer within a fraction of a second, it's too late to get it. You don't need it anymore. So data analytics then, reliable and robust data acquisition from sensors is very important, because if your data is incorrect, then everything else is incorrect. You need to enhance your signal, because the data that you get may have a lot of noise and may have interference. So you have to remove the interference, you remove the noise, and enhance the actual data. Then you extract features. So fields in data analytics includes feature extraction. Then you look at patterns within that data, pattern recognition, classification and decision support systems. And we do have courses in all of those areas. Then reliable sensor data fusion, because you may have sensors coming from sensors deployed everywhere. You get data from those sensors. You have to determine how reliable those sensors are. So for example, if you have a drone, and that drone has got a number of sensors to tell you, whether an obstacle is there and so on, some of those sensors may work extremely well in some conditions, and some other sensors will work really badly. I'll give you an example. In the case of a drone or aid for visually impaired or cars or robots, and you want to do collision avoidance, if you have infrared sensors and ultrasonic sensors embedded there, you will find that infrared sensors work really well. However, if you have a glass obstacle, the infrared sensor will not detect that glass. So it will just jam into it. Whereas if you have ultrasonic sensor, it's not as good as infrared, but it detects glass. So you can combine information from those sensors and determine the reliability of those sensors, and then be able to come up with something that fits your need. So if you fuse the data or combine the data from all of those sensors, you can come up with a far better solution. And if you're aware of the context you're in, like if you're relying on a camera and it's very dark, then the information is not going to be that reliable. So if you have a light sensor that then tells you, now in this context, that sensor is more reliable than the other, then you combine the information and get it. And finally, one very important task there is the proper user interface and all of the human-computer interaction involved in there. So sensors and data analytics applications are everywhere, including infrastructure monitoring, bridges, roads, power grids, pipeline infrastructure, and we have some posters dealing with those. Professor David Lau has got something on bridges and roads, and there's a presentation going there. Intelligent aerospace, to improve the performance and safety of airplanes, to reduce the noise in the cabin, to have the engine run more efficiently. This requires sensors deployed there everywhere to have the planes run smoother and better. Now, safety, security, and infrastructure protection, medical application, automotive application, environmental monitoring. So these are the engineering applications, but there are applications, as I said earlier, in each and every discipline that I know of in terms of whether it's politics, whether it's journalism, whether it's biology, whether it's chemistry, whether it's arts, whether anywhere there, I think we're having more of this. So I think I'll stop here, and maybe we have time for a few questions before we go into the panel. Yeah, this is a very important issue where essentially, where is the processing done? So you have sensors. Let's say you have wearable sensors. So is the processing in terms of determining the clinical information, is it going to happen at the sensors themselves, or is it going to happen somewhere in the wearable system? Or maybe the information will go into a hub and the decision is made there, or sent to the cloud and the information is there, or the analysis is done there. This is a very challenging issue because you have to look there at power consumption, you have to look at reliability, and you have to look at communication link versus processing, because sometimes the sensor generates a tremendous amount of data. So do you need to transmit all of that and then analyze it elsewhere? Or do you want to do some pre-processing at the sensor to reduce the amount of data and then send less data? So it's a compromise between communication needs, between processing power, reliability, and everything else. So it's application-based, but there is, in addition to what I talked about, there is the whole area of software architecture that allows you to handle this and the cloud aspect as well. Okay, so data analytics and big data in general is not a field that's the responsibility of one unit because it spans each and every discipline that I know of. So now I guess we have the collaborative masters in data analytics where students who are in a specific program can go and take that in addition to their degree. So they have a degree in area X, and then you add to it the data, big data, data science, or data analytics aspect. But we're also thinking of very specific programs that deal with data analytics, where you get a master's in data analytics. So we're working on that right now, where you would have students in specific disciplines going in and having a full degree on data analytics. But as I said, the algorithms and the approaches to handle big data are different, whether you're talking about real-time, time-restricted and time-limited data analytics versus big data. And the two deal with huge amount of data. But then I guess there are distinct programs that handle this. But also, I guess, there are seminars and there are various research projects dealing with data analytics going from the Faculty of Engineering and Design. When I talk to people in mechanical engineering sometimes or aerospace engineering, I said, what are you working on? A new faculty member came in and I was asking her, what are you working on? And she said, well, I have sensors in the engine to measure noise and vibration. And then based on that, we're making, feedback decisions and we're trying to remove noise. So essentially, she's working on data analytics applied to aerospace. Professor David Lau has got those sensors deployed on the Confederation Bridge and then measures wind, vibration, and so on, and then make decisions accordingly. So this is, again, data analytics. So I guess we have, throughout the university, many, many projects where people don't think they're working on data analytics, but in fact they do. So anything, Jim, you want to add?
Perfect. Thank you for the ad. Stay here then, I'll just to, I forgot earlier, just to give you an idea of the construction for the day. You've seen the program. There are four main sessions. One is the graduate student poster session outside. Whenever there's a free time, please go and look. The students have got some really wonderful presentations there, and they will be judged, and valuable prizes will be afforded to those right students, the winning students, thanks to our sponsors. There's three other sessions. One is the one that Rafik just started, and that is a snapshot of some of our Carleton researchers and what they're doing in the general area of data science and analytics. Just to give you a taste, you know, there's probably many more people doing that across the campus, but gives you an idea of the variety of the discipline. Secondly, the second session after the coffee break will be for outside users and their needs, their challenges, what they see from private sector through to government. Everywhere you look these days, people are talking about needs. And so as Rafik just pointed out, that's our job, is to try and fulfill those. But what are the opportunities for all of us? And then after lunch, which will be done outside, I ask you to go through the poster session, visit our guests, and there is a free lunch, by the way. I'm sorry there's no free parking, but there's free lunch. That's how we figure this. And finally, this afternoon, we have a special session on data science and analytics in the social sciences and humanities, which is probably the domain where, in fact, most needs are emerging right now. And there will be a panel on that led by Dominique Beyroube, who is Vice President Research at the Social Sciences and Humanities Research Council. So that's the day. If you get a bit, you need a little bit of a walk, remember this session is being live streamed outside. And if you need to go outside, if any of you, as Jim mentioned, want to meet anybody, we can provide a space. And I'd now like to introduce someone you've never heard of before, our Dean of Engineering, Rafik Goubran, who will chair the session of our researchers. Thank you.
Thanks, John. So I'd like to invite the speakers maybe to come in the front. So please go ahead. So we have Paul Villeneuve from the Department of Health Sciences. Paul. Then we have Tracey Lauriault from the School of Journalism and Communications. So Tracey's here. And we have Olga Baysal from the School of Computer Science. And we have Mohamed Ibnkahla from the Department of Systems and Computer Engineering. So now every one of the speakers is going to be talking for about 15 minutes. And then at the end, we'll have a chance to have questions. And I'd like to ask the speakers to introduce themselves very briefly at the beginning. So maybe we'll start with Paul. So would you like to? Yeah.
Good morning. I'm Paul Villeneuve. I'm an associate professor in the Department of Health Sciences. I've been at Carleton for about 2.5 years, and before then, I was a research scientist in Health Canada for about 10 years. Anyways, I'd like to thank you for the invitation to come today. I've already learned some great ideas about some potential research based on the first talk. I'll think of breaking in a different way as well now too. But anyways, I'm happy to be here. And I'll be talking a little bit about some applied research that I'm doing in the area of environmental health and data science. So much of my research focuses on environmental and occupational health and the effects of air pollution. Now, when we run across air pollution in the media, generally we get pieces when there happens to be high episodes of air pollution, whether it be in Beijing or other parts of the world. So not all the times these headlines will be necessarily accurate, but you can get a sense from this slide about some of the messages that are being delivered. And in terms of much of the focus historically on the health effects of air pollution, they've looked at the short-term increases of air pollution based really from the Great Fog in London in 1950, where 12,000 people died when there was high episodes of air pollution over a few weeks. So before I get into some of the research and how it relates to data science, I thought it'd be important just to go over some of the different air pollutants we study. So as you can imagine, we'll have area sources of air pollution, sources from forest fires, from traffic. Much of my research happens to focus in on fine particulate matter air pollution. Now, to give you a sense in terms of how small these particles are, on the slide you'll see a strand of hair, And if you were to slice that strand of hair, you could see that you'd get about 4 to 6 of these particles going across the diameter. So they're very small particles that can be inhaled into the lungs and can cause a number of adverse health conditions. So in terms of the health impacts of air pollution, a couple of years ago, a global burden of disease report came out and indicated that air pollution, long-term exposure to air pollution, accounts for about 3 million excess deaths per year. It's one of the top risks worldwide, and especially in some countries that are developing where levels of air pollution are much higher, it ranks much higher. So you'd think of things like tobacco, diet, physical exercise. And a couple of years ago, the International Agency for Research on Cancer declared fine particulate matter air pollution to be a carcinogen. So air pollution is extremely relevant, and going forward, it's projected to be one of the top causes of environmental-related deaths worldwide. So this is kind of one of the main reasons that we study it. And in terms of the health effects from short-term increases versus long-term, we've done a number of studies, time series studies, where we look at daily changes in air pollution levels in relation to daily changes in mortality. And we've also looked at longer-term exposures to air pollution. And generally, it's now well understood that the long-term consequences of air pollution are much more harmful. It's related to a number of different health conditions, from atherosclerosis, diabetes, hypertension. So it's widely studied in a number of different contexts. So getting back to some of the research that we're currently doing, we have a number of large Canadian cohort studies that are looking at the health effects of air pollution. The cohort studies are really important because they give us a sense in terms of how long-term exposure to air pollution will change things like life expectancy. And in terms of the data, because the effects are relatively small, especially in a country like Canada, where air pollution levels are much lower, we need very large populations to begin to understand some of these different health effects. So this slide just gives you a sense in terms of how much lower air pollution levels happen to be in Canada versus the rest of the world. One of the nice things about doing research in air pollution in Canada is we're able to do record linkage studies with large data sets at Statistics Canada, with Health Canada. We have a lot of different types of exposure data that we're able to assign to these individuals in these studies, and I'll get into some of the newer exposures that we do have. And we're also able to look at a number of different health outcomes. So this is a design of some of the types of cohort studies that we've been conducting. So typically what we'll do in these studies, we'll get cohort data, and we've used cohorts like the long-form census data in the past, where 20% of Canadians have to fill out the census data. We'll link that information to annual income tax filings. So that allows us to identify people's residential mobility over time by their postal codes. Then we make use of exposure surface from things like land use regression surfaces, where we're able to create contours of maps within various cities. We're now able to use satellite imaging data to assign levels of PM2.5 to people's places of residence. So in addition to that, we're also linking the cohort to mortality data, cancer incidence data, so we're able to follow people up over time, account for their changes in air pollution, and look at what types of health outcomes they identify. So I spoke briefly about one of the studies I've been involved with, the Canadian Census Cohort. So in this study, we followed up individuals who completed the long-form census in 1991, so 2.7 million individuals, and we followed them up over a 10-year period, and we linked information to mortality and cancer incidence. So in Canada, this would involve linking the 2.7 million people on an individual level basis to mortality, where we have about 270,000 deaths a year annually, and cancer incidence, where we have over 200,000 cancers diagnosed. So in addition to this, we also collect from Canadian census data information about neighborhood variables, income, lone parent households. So you can imagine the volume of data that we're using to create this cohort is fairly extensive. So in terms of assigning air pollution exposure, we'll assign it to people's 6-character postal code. And we'll get the latitude, the longitude of the centroid of the postal code, and we'll assign estimates of air pollution. So this is a slide that shows concentrations of air pollution in Canada for fine particulate matter. So this was developed using remote sensing technology, and we've published a few papers on this, showing that even in Canada, where the air pollution levels are fairly low, we're still finding increases in mortality of about 30% for a 10 microgram per meter cubed increase in PM 2.5 for things like cardiovascular disease mortality. So what's important to keep in mind in terms of one of the benefits of using the satellite imaging is that in the past in Canada, we've relied on information from Environment Canada's fixed site monitoring. The satellite data offers the advantage of being able to assign air pollution values to anyone in Canada, regardless of where they live. In the past, we would have been constrained by people having to live within a certain distance from these fixed site monitoring stations. So how this works. So here we have a view of Earth from space, and then through the satellite imaging data, we get information on aerosol optical depth. So we're able to come up with estimates of this aerosol optical depth. And you'll see in the slide here what some of the pictures might look like if we have increased levels of fine particulate matter air pollution, what some of the pollution haze might look like over parts of the US. So we generate, or some of my colleagues who are atmospheric scientists will generate these surfaces of aerosol optical depth over a time period. Here you'll see it generated for North America, but they've generated these surfaces worldwide. And then they make use of a chemical transport model. So this allows us to incorporate things like meteorology, atmospheric chemistry, and through this simulation, they combine this with the estimates of aerosol optical depth. And they've found that these surfaces correlate very well with data that are obtained from 6 fixed site monitoring stations that are operating continuously on the ground. So in terms of some of the computational challenges, they're retrieving a large volume of data. There's a lot of nonlinear modeling that has to take place to come up with some of these estimates. Right now, the PM surfaces are being generated at a resolution of 1 kilometer by 1 kilometer across the world. And in terms of some of the expected growth, in terms of the data over the years, climate change data, and including some of the data obtained from these satellites, is expected to grow substantially over the next 15 years. And this just gives you a sense of all the different types of satellites that are out there that we're retrieving data from to generate some of these surfaces. And another consideration as well, too, the slides that I've presented so far and some of the studies that I've described have looked at longer-term estimates of air pollution in terms of mortality. But they are also taking some of these data from the satellite imaging and trying to come up with estimates of air pollution at finer spatial and temporal variations. So a lot of the surfaces we've modeled so far have been 5 or 10-year estimates of air pollution. Now we're actually getting to a stage where we're able to account for some variations in PM 2.5 over shorter time frames, weeks, days. It's constrained sometimes by cloud cover, but the methods are being refined to get more enhanced data. So in terms of additional needs, we are looking at other types of environmental exposures at the same spatial scales. I'm involved in some studies looking at the impacts of greenness in urban areas and how that's related to things like physical activity. Some people are modeling nighttime light in relation to some health outcomes, because a lot of these environmental exposures, whether it be green space, air pollution, urban noise. They're all linked to some extent, so it's important to have these surfaces that allow us to look at the effects of all of them. And as mentioned in the first talk, we're also starting to incorporate some new technologies in terms of trying to get better sense in terms of how people move around a city with GPS devices, in terms of measuring accelerometers, physical exercise. So it will allow us to look at associations between some of these environmental exposures and some of these health measures in a real-time basis. So I'd just like to mention some of the collaborators on this study, of the census study, Randall Martin and Aaron Van Donkelaar, who've developed a lot of the surfaces at Dalhousie University, and as well people from Health Canada and Public Health Ontario. There's my email if people have questions, and one of my students also has a poster outside, so I'm hoping you are able to have a chance to visit that as well. So thank you.
Morning, everyone. So we're the new kid on the block when it comes to the Data Science Institute. So we're the department, we're the School of Journalism and Communications. And what I'll do today is I'll just go over a little bit of some of the research I've been doing and the way that I look at data and the way that I look at data analytics. And in a way, you might say that people like myself, we study the people who do the data analytics and to try and understand culturally how they do things and how they go about doing things. So from a data studies perspective, what we do is we try to understand how data analytics come about, who produces them, the kinds of algorithms that are there, are there any politics or cultures or values embedded in those algorithms, what kind of software, who are the purveyors of those software, what do they do, what are the consequences of the use of data analytics and embedding sensors in space, and so on and so forth. How do they augment space? What does it mean when you have sensors that are deployed in a smart city kind of context, and what does it mean for the politics of a city when that actually happens? Who becomes the mayor? Does the data analytical system become the mayor? Does the software company or the large platform company become the mayor? How do politics get negotiated when you have a smart city and you become very data-driven? Do you become solely data-driven, or are you able to actually mix mechanical objectivity with some kind of qualitative subjectivity in the sociology and the anthropology of how we live within our spaces? One of the projects that I worked on, and I've just come back from Ireland last week, is called the Programmable City Project. It was funded by the European Research Council. And what we were looking at was, how is the city translated into software, data, and code? And then how does that software, data, and code inform or change the city in any which way? So what we're looking at is, how do these analytical systems socially shape, culturally shape, politically shape, and technologically shape the city, and how do we in turn change and shift accordingly as societies, as people, as politics, and as cities? The way that I look at it, and of course I won't go through all of this in detail, but what I do is I look at the context. I'll look at the politics. I'll look at systems of thought. I'll look at mathematical backgrounds and scientific backgrounds. I'll look at how things are actually done. How does IBM do it? How does Cisco do it? How does Intel do it? How does Siemens do it? How are these things financed in the political economy? How is this regulated? What are the laws pertaining to these kinds of things? And Rafik gave us some issues with regards to hacking and being able to hack your smart home, for instance. What are the cultural predispositions of the people who come into these environments? What does it mean when you have a data scientist, a social physicist, and a sociologist, and an anthropologist, and a public servant working together in this kind of space when they're actually informing decisions? But as I'm looking at that context, I'll also unpack it a bit more, and I'll look at the actual technologies themselves. How is it operated? How is it used? What's its interface? What kind of algorithms in software code are being used? What's the life cycle and the flow cycle of how the data move through those systems? What's the database like, the platforms, and the material platforms? And all of this fits into new emerging types of studies that we're seeing in the humanities, we're seeing in communications, we're seeing in media studies, and that is either platform studies or surveillance studies, critical code studies and software studies. In those spaces, we might do things like algorithm archaeology and follow the algorithms through time. And in my case, what I look at is critical data studies. And so I try to unpack the nuances and the subtleties of data when they're deployed. The other way that I also do it is I also look at how is knowledge produced. For instance, how does a classification become a classification? How does a classification become a fact? And how does that fact get used in the world? And once that fact and those individuals and those places have been labeled according to that classification system, how do they resist it, or how does that place change? So in the philosophy of science, we have a scholar named Ian Hacking, a Canadian who was one of the only few Canadians and an Anglo-Canadian at the Collège de France where Michel Foucault studied. His methodology I've adapted to try and help me understand the subtleties of how we make up spaces and how we make up people through analytical types of processes. So to show you a little bit of how that works and to make that accessible, I'll go through the 3 case studies whose data I'm looking at right now. So one is a study about ontologizing the city, and that is a project with the Ordnance Survey of Ireland. The Ordnance Survey of Ireland has gone through a massive transformative socio-technological change whereby they went from old school cartography to an object-oriented real-time database system. So they moved from near analog, simply imagery, towards really into a big data environment. And I spent a month and a half of my time in the organization speaking with about 25 of the key players who were developing the data models to understand what it is that influenced those data models, how were those data models deployed, why were those particular technologies used, and how is the institution radically changing as a result of it. But in addition, how are we rethinking about space? How are we rethinking about cities? When you reclassify a place, when you re-ontologize a place, it means that you rethink about a place in a very different way. In this case, their model it's an Oracle-based spatial Oracle model called Prime2, developed over quite a significant amount of time, and it completely redefined how space is understood. In the Ordnance Survey, it used to just be a series of maps, and every time you had to update something, you had to go back to each sheet and update each element in string and dot and line and polygon. And now they've moved completely to a data model, so a topologically accurate, reliable, and updatable in near real-time type of system that is really quite transformative in terms of how they do things, but it's also changing their entire flow line of the organization. What they used to do is they used to have these old hand-drawn maps that they scanned, and then those scans were rendered into lines that weren't connected into polygons, and those were changed at different kinds of scales to the point where now it's starting to look like this. And in fact, we rarely get to see a map anymore. And in fact, with the Ordnance Survey, you don't even have to interact with the organization through a map. You can simply interact your utilities institutions through the database. You can connect with all of the lighting systems and the smart city systems that are being deployed and different sensors that are being deployed as part of the smart city program in Dublin. This is revolutionary in cartography, and it's revolutionary in national mapping, and I had the good fortune to spend some time with them. But as I discussed, I also look at the context. So I looked at how it went, the institution, the Ordnance Survey in Ireland, went from a colonial surveyor to a state body national mapping organization. I look at how it's changed technologically in terms of how it's kitted up differently, how people have to use tools and technologies differently, but also the scope from colonial mapping to national mapping to post-colonial mapping to regional mapping with the Ordnance Survey Ireland and Great Britain, and then how it's connecting with the EU, INSPIRE, and national spatial data infrastructures and global spatial data infrastructures, and how this little teeny tiny place on the map in so many respects has become a global leader and player in the way that they have reorganized and restructured their data and how they do things. But you still, even in the new model, you see traces of the old. You see the old ways of mapping and the old ways of doing things very clearly embedded into these particular systems and into the actual current ontology. And in fact, the old way to model the real world understanding and the new way of model are very intimately intertwined. Generally, when we see a data model, we see it finished and we see a fait accompli, and we can't imagine the world in any other way. But in fact, the world was imagined in a very different way in that institution, and the way that they constructed that world was also very different. The model, in the context of a data model for the Ordnance Survey of Ireland, goes back into 1999, and it continued to evolve with multiple collaborations and seminars and workbooks and workshops and institutions and themes, to the very recent ones of just Googling and doodling on whiteboards, looking at real objects, trying to abstract things from those real objects, but most importantly, all of these data models, while we see them technologically mediated, were all created and socially constructed by people and the way that they understand the world. So what I look at is how the people construct their world through data. In the context of the Ordnance Survey model, this is one quick abstraction of it. It starts in 1999 and all the way to 2015, but that whole assemblage includes requirements documents and specifications and workshops and different technologies and different server types of environments. Even everything to the procurement officer has been actively involved in the structuring, the creating, and the production of this particular model. In other words, models don't come out of nowhere. Models shape how we view the world. They model how we do work in the world. They model the techniques and the tools that we use to understand and track and sense the world, if you will. Models also shape and structure an organization, and these models also shape how the organizations interconnect with other organizations and other institutions. So they augment space, but they're also, as I said earlier, socially constructed by people who have different tools. And in these images that I'm showing you here, these are the old model and the new model and the old technologies and the new technologies beside each other. The shift has just happened in Ireland in the last year. And these were them walking us through those particular systems. But other examples that I might look at, I also look at, and this is another case study that's based in Dublin, it's based in Boston, and it's based in Canada, where I'm looking at how are homeless people constructed through databases. So what I do is I look at the intake systems at the shelter that are used and how the classification systems shape different and track different people who go into those shelters. But I also look at street counts, because all these different jurisdictions actually do, at certain points of time of the year, actual street counts of people sleeping rough on the street. And then in each case also, officially, the official census also tracks who are homeless and homelessness. And what's very fascinating is if you go simply by looking at the data, what we would have conceived as a homeless person, or how we would have imagined a homeless person in our mind, is not the same homeless person if you look at the data shadow and you look at the data trace. They are constructed very differently because of regulation, because of context, because of culture, because of institutions, because of financial situations and social support services, and also, of course, demographically, depending on the kinds of context. And so I spent quite a bit of time speaking with all of the actors involved in this space to understand how that gets constructed. And finally, the last case study that I'm looking at the moment is I'm looking at open data. But when I look at open data, I don't just look at, let's make an app and look at a data portal for the moment. I try to go back at where do the origins of this concept of open data come from, and what are the other aspects of open data that are tied into that assemblage. So we know that open licenses is part of the discourse of open data. We know that open source formats and specifications are part of the open data space. We know that open infrastructures, whether it be Earth observation infrastructures, research data sharing, or whether it be archival infrastructures, are also part of making those data accessible and available and open to us. But we also know that the definitions go way back. I started 1959 with the Continent of Science and the Antarctic Treaty that was the first that say, if you're going to do any kind of research in Antarctica, thou shalt share your data. Otherwise, you don't get to do research in that area. And then there's the Agenda 21, the 10 years after. The Open Knowledge Foundation tends to be the definition that we refer to the most, but also the latest 5-star and linked data types of definitions that are emerging in terms of open data. So in other words, we think we understand what open data are, but in fact there are many views and many lenses to look at open data, and depending on which lens you use, which definition you have, will define how you look at open data differently. Concurrently, there are data cultures. There is no one data culture that is the same. In the open data space, the early cultures would have been physical sciences, social sciences, and to some extent, people who were doing early crowdsourcing work and citizen science work who were collecting data in space. With time, we start seeing geographic data, such as spatial data infrastructures. We see government data and administrative data. But each of these communities has a very different work environment, has a very different culture, has a very different epistemic lens, or a very different knowledge structure by which they see the world. And what I want to understand is, how do these people come together to understand this notion of open data, and how do we work together from these different types of cultures, and how do these different cultures inform the discourse? And so, to conclude, just to let you know that we have joined the Data Science Institute. We'll have our first master's students start with us next year. The students who would come into our program would do Communications 5225, which is a critical data studies course. And some of the students are here, and you may see some of them during the break or at lunch, so by all means talk with them. They'll give you an idea of some of the things that they've been learning. The students would also participate in the transdisciplinary environment with the more what we call the quants, or the more quantitative side, or the more positivist side of the data science program. And so our students would be participating on that side of things, but then they would be looking at things such as communication, technology and culture, internet infrastructure and materialities, and science and the making of knowledge. So a very, very different perspective on data science, but I think very mutually supportive, and should be very, very interesting to see how the collaborations go in the next few years. So thank you very much.
So good morning, everyone. My name is Olga Baysal, and I'm from the School of Computer Science. I've recently joined Carleton, and this is my first year. And I'm really, really being excited here, especially that I'm currently teaching the data 5000 together with Boyan. I'm not sure if he's here. Yeah, Boyan is there. So we were really, I would say we are privileged to teach our data science students, and I can see quite a few of them here. And we have at least 2 teams presenting poster sessions. The posters research over there, Kevin and Ardeen, and I think another somewhere, George. So yes, please check them out at the end as well. So my research area is really focusing on software analytics, and I will just give you an overview what software analytics are and just try to highlight some of the opportunities and challenges that this area is facing. Also, I will introduce some of the projects that I currently work or have recently worked on. So software companies, many IT companies, they generate very massive amounts of data, such as source code, documentation, different version control systems, bug reports, test suites, and any kind of documentation. Also, our software developers are quite social. They go to Twitter, they generate massive amount of social media via Twitter, for example, or they blog. Developers are quite, very active in being bloggers as well, and as well as they go to online as well and generate any kind of, by developing software forums and such, Q&A forums, and also being quite active online. So all this data, all these artifacts, all these kind of repositories, software repositories, they're being created by many organizations. The high-level problem here, as with any data, is that information that is contained in these artifacts and these repositories is not presented in a way that is immediately useful for different stakeholders. And that is, the data is not actionable. While successful software companies, organizations, they expect different stakeholders making a variety of continuous decisions. For example, managers trying to achieve business goals, sales teams trying to increase companies' revenues, release managers trying to ship products on time, and software developers trying to build error-free software systems. And the understanding of their systems are driving their decisions currently, which is not really optimal. Such decisions can be quite risky because they're based on their experience, on their intuition. These decisions might work sometimes, but in reality, they're not data-driven. So, one of the solutions that we are dealing here is just applying analytics to the field of software engineering and trying to use data science or data analytics, whatever the term you prefer to use, and just dive and analyze these massive amounts of information, trying to extract useful information so we can support our decision-making of different stakeholders. So what is software analytics? Software analytics is really the data analytics. It's really the process of gathering the information, curating the data, analyzing the data, and making sense of the data. And here is a very basic cycle of the data science that we are teaching. So you start with data mining, you apply different statistics, you perform your analysis, and then you interpret the results, you try to build different applications. You can build recommender system, different predictive models, and then you leverage these insights by incorporating this into the processes. So in short, software analytics is making sense of the software engineering data. And thus, with software analytics, we can provide data-driven decision-making to different stakeholders, as I mentioned, and it's really about providing the facts on the system that can help us to improve the processes, software engineering processes, as well as practices. And I will show you a few examples so it will be clear. So the type of research projects that I'm involved, they relate with software engineering. So first, I would say we perform the data science, but we don't just stop at analyzing the data. It's very often that we design an application or design a tool that can be used. And this is a few of the projects that I'll be talking today is designing and developing analytics for developers in particular, such as developer dashboards, as well as some API analytics for online forums, for example, Stack Overflow, and improving some of the understanding and improving some of the software engineering processes, for example, code review, as well as some of the a project that grad students in my last grad course were working is about really exploring the opportunities that the social media is offering by mining the Twitter data. So I will start with the analytics for developers. So here you can see that there is a developer dashboard. You can see, well, this is very different from the type of dashboards that we used to see. So majority of the dashboards are very quantitative in nature. We provide, chart-based views, some performance data, some kind of graphs. That type of analytics are really geared towards project managers. I'm not saying that these analytics are bad. These are good analytics. But once we talk to the developers, and in all our studies, we really closely working with developers. This project was done with Mozilla in Toronto office, and we interview developers. We get to know them. We get to know their problems, what kind of challenges they're facing by using the tools and environments that they have to work on. And from talking to them, we understand the challenges that they face and the problems they have. And then we design the solution specifically for the type of challenges they have. And then again, we go back to them, we evaluate the tools. So this is the type of dashboard that they want. And you can see it's quite different. It's not a very fancy graphic kind of dashboard, but this is the type of dashboard that developers want to see. This is more qualitative in nature. It really helps developers to increase their productivity, but as well as their situational awareness. Situational awareness is really the awareness on the project, on the type of tasks that developers are performing daily. Either they are tracking the status of the issues that they're working on, either they are shipping their patches, or they're performing different tasks such as code review. So this kind of dashboards helping them in achieving the task, in prioritizing the issues, and being alert on the type of task that they have to be working currently. For example, here the dashboard will highlight if the patch was staying there for a while. It will just highlight that, okay, pay attention to me, you might be addressing me shortly. Or if the review has been pending there for a while, the type of review will be telling me, okay, pay attention, I've been sitting here for a while. So this really is providing the personalized views of the kind of repositories they're dealing with. The data is there. We are not creating the new data. We just use the data and present it in a way that is useful to the developers. So probably you've heard of the Stack Overflow, and whenever you have any kind of problem, or developers, they often go to online help. So for example, if they don't know what kind of API they would like to use for the type of problem that they have, they go online, they go to Stack Overflow, they type a question, and they try to search for an answer. And again, here we're facing with the information overload problem. So there is so much information, so much advice over there, and how do you know which advice is really relevant to the task that you're dealing with? Or how do you know which API, if there are many varieties, which solution actually to your question is more relevant? So this type of research is focusing on opinion mining and summarization. So one of the students is currently, Gias is working on providing help for API opinion mining. So here you can see that, for example, this is a Stack Overflow post, and it will really give you just a plain text while he's trying to identify the API mentions and connect it to an actual documentation, to the formal documentation. As you know, any kind of information is very informal and it's very unstructured. So the challenge here is how do I identify the right information and link it to the actual documentation so developers can grasp the information quickly. And again, opinion mining, the sentiment analysis here is important. So you want to be able to get the insight which API is more probably better to use in certain cases, and which ones probably maybe lacking some security support or something like that. So it's also important to understand which information is more liked by other developers. Another area is really understanding the software engineering processes. For example, here, code review is a very essential process in software development companies. Code review is the process of assessing code changes that they are submitted before they actually shipped to the master repository. And this process is especially important for open source communities, where contributions in the form of patches can come from anywhere from the greater user community. So what we're trying to see whether code review is by design has to assess those contributions before they're submitted. But the main question here, so how well actually the code reviewers looking at the patches? So what is the quality? And our question at this recent study was, so how much of the bugs actually code reviewers missing? And we performed the study again on Mozilla project, and we found that about 54 to 56% of code reviews are actually quite of poor quality. And this really raises some flags. Not only we look at how much they actually miss the bugs, but also what are the factors that affect code review quality. So we look at the variety of factors that we could extract by mining the data that is being collected, and we find out that both technical specification of the patch as well as personal attributes of the developers, they do affect software code review quality. Recently, we conducted a qualitative study where, we know that the data doesn't represent all the factors that might affect our processes. For example, culture, organizational structure can affect quality as well. So we went back to the developers, we surveyed them, trying to understand what are other potential factors that might influence review quality as well. So we really look at the developer perception this time and their attitudes toward code review quality, and try to see whether there is any gap that we are missing while really having a complete and overall picture on this topic. Social media, as you know, for example, Twitter is getting quite popular, and it's really generate enormous amount of information that can be really used to extract very, very useful insights from our everyday lives. And one of the applications that we can use and utilize the Twitter data is really, for example, from to help the healthcare sector by detecting and surveilling infectious diseases. So one of the projects that some grad students, Ken and Alisher, has done last term is they look at the Twitter streams, they analyze the Twitter streams, trying to classify tweets according to the sentiment, according to positive or negative sentiments on the flu, and trying to see how whether we can detect the flu and see how the flu spreads. So here you can see the interactive application that they developed, showing how the flu originates and how actually it spreads towards, they look at the Toronto, Ottawa, Montreal, as well as New York regions. So this kind of analytics is really useful, for example, for healthcare sector, where you want to monitor quite instantly of how the diseases are spreading. So I think it's really nice to mine the data, especially the so rich social media data, in order to answer a variety of questions. So the type of opportunities that software analytics are offering is really that we have plenty of techniques, plenty of tools, machine learning, any kind of tools to get the data, to analyze the data, to process the data. So we have all these techniques that we can get insights, we can understand the trends, we can identify the patterns within the data. It's really, we have this tool support. So we can offer different stakeholders better understanding of their systems, of their processes, as well as they can track the evolution and how their systems progress. But the main challenges are really associated with that the data comes in very different forms. It's really, sometimes it is very structured, but in many cases it's unstructured. And we have to process the data, we have to curate the data, and we have to massage the data, and usually it takes quite a big amount of time to spend on this type of tasks. And we have a variety of data. In order for us to have a complete picture, often we have to correlate different repositories, different artifacts together, which might not be quite trivial. And this is another challenge, that it's good that we have the variety of data, but correlating different pieces can be a challenge here as well. And sometimes, developing different analytics, extracting insights, we can get the results, but we are not quite sure how these results can be used. So what are the implications of the type of studies we perform here? This is another challenge. Designing and engineering analytics tools can be also challenging. These tools, as we notice from our experience at least, that they have to be easy to use. They have to be simple. Developers or project managers, they don't really need a complicated and complex tools. They want easy solutions. They want an easy button that they click on it, and they can get insights, and they can tell what the data is actually telling us. And another challenge that we at least faced in our studies is the adoption of the type of prototypes that we develop by industry. Because for us, we are dealing with the research setting, but once we have to deploy our tools into actual industry, this can be also a quite bumpy road. So here is my wish list. Here is that I'm new to the community, I'm new to Carleton, I'm new to Ottawa, and what I'm looking is really for some collaboration. And using this opportunity of the great audience here, I would like to invite anybody who is interested in working on the type of analytics that I've mentioned and beyond. Please talk to me during the coffee break. I'll be happy to listen to your problems and how we could possibly resolve those. And software analytics is quite an emerging field. And with my colleague Latifa, we organized a workshop on software analytics last year that was held in Montreal. And we are continuing this research just to create our own research community on software analytics. And we are hosting the second edition of our workshop on software analytics. This time it will be in Seattle, and we have our website, softwareanalytics.ca. Please, if you're interested in submitting or sharing your ideas, check out the website, and more details will be posted there shortly. That's all for now, and again, I'm really invite you to go and talk to the students. There are many 5,000 students here, our future data scientists, and they have very interesting and exciting research proposals, and please go and talk to them. Thank you.
Okay, so good morning, everybody. My presentation today is about the Internet of Things, so I'm happy to be the last speaker here because you have now a good background about what sensors are and data analytics is. So basically, I'll start first with an introduction about the Internet of Things and its potentials, and then I will present the Internet of Things ecosystem as a multidisciplinary field. The difference between Internet of Things and machine-to-machine communications, and then big data and value co-creation that can be actually generated out of that data. And then I will make some concluding remarks. The Internet of Things is actually about connecting everything through the Internet. What we have seen today, the speakers have mostly focused on the sensors, on the analysis of data. But what's important also is to connect objects, make them speak together, make them talk to us, make them have an autonomy and deliver the data and knowledge they have. So the Internet of Things is about connecting objects and exploiting the information that is actually generated by these objects and these sensors. So the system is used to sense, report, control, and also perform other tasks that we'll cover in this talk. In terms of size of connected objects, Ericsson and Intel experts expect to have about from 50 to 200 billion objects to be connected by the year 2025. So it's really a huge number of objects connected. General Electric expects they estimate the global economy related to the Internet of Things to $82 trillion. So it's about 1/3 of the total economy on Earth. So here they mean by that the related area or the related field of economy that is connected and using the Internet of Things. Cisco, they have made estimates about the Canadian market, and they estimate, the estimate is about $400 billion to the Canadian private sector in the next decade for the Internet of Things opportunities. And they estimate also $95 billion savings in productivity and marginal cost for the government. So this is only for the governments in Canada. $95 billion savings in marginal cost. So the marginal costs are due to, for example, to the logistics, to transportation, to time spent on searching things, etc. So the savings, just the government only, is $95 billion over the next decade. So the vision of the Internet of Things is really to allow real-world objects to communicate, to connect, and interact the same way that we do today with the Internet. We can search, we can Google, we can check our bank accounts, etc. Tomorrow, it's objects that will do that, so that when you drive your car will negotiate the price of gas or electricity recharging. It will pay directly. It will optimize the route for you. It will make some recommendations to your children to stay at school, wait for you, or to even negotiate buying groceries for you to optimize your time. So it's really objects that communicate with objects that communicate with humans. So the Internet no longer will be with people, about media and content, but also it will include real-world assets as intelligent entities. So a chair, a room, a car, a street, a highway, all of them will be intelligent entities that can talk, that can negotiate, speak, and give some recommendations. And of course, we have this value co-creation. We have co-creation of knowledge and business process that will be generated out of that. So if we can, if I may here give an overview of where we situate ourselves and where the big data is and where sensors lie. So in the bottom here, we have the device level that Rafik has very brilliantly explored and presented to us. So we have the sensing, we have actuation, we have tags, signal processing, and we have some data management there. So part of the big data is here. Okay, it's not only the whole story, but part of it is here. As Rafik mentioned, part of the processing can be done at the device level. And then we have what we have here. We have the system management, configuration of system, reporting, membership, and so on. We have communication, which is also very important. We have networking, we have medium access, we have applications. And then we have here mostly services and data analytics. So in terms of data analytics, they are here and they are there. We are at the device level and also at the application and service level as well. And then we have security. So security is really very, very important, and it has been highlighted by the previous speakers. It's all over the board. It concerns the applications, access, concerns the physical devices, it concerns spectrum, the data itself. So it's really, security is all over this multidisciplinary field. And then we have applications. We can have standalone applications. We can have complex applications that are actually composed of many other applications, and we can have business-oriented applications. And I will try to highlight a little bit what these mean. So here, if we look at data analytics, is almost everywhere. If we look at communications, also it concerns every aspect of the Internet of Things and device communication. So here, when we talk about value co-creation, we mean by that a user that is not supposed to use the data, but it can make use of it, whether in real time or later after 1 year, after 2 years, after 10 years. So what's important here is that Internet of Things experts and business experts tell us is whatever data you can store, whatever data you can collect, keep it, collect it, because you never know, probably you will make money out of it, you can make business out of it later on. So as long as you can store data, you can collect data, please do so. So here, as you can see, for example, you have user one, which is the owner of the data, the owner probably of the devices, will actually be able to collect that data. So we have the IoT service here, and then we have data analytics for that particular user. For example, it can be a utility company that is, for example, measuring the electricity consumption in a house. So the electricity company will make data analytics and analysis of data, use how residents in Ontario are using their data and so on. However, another user can make value of that data, can make a business out of that data. It can be, for example, the city of Ottawa. It can be an insurance company. It can be the bank. etc. They can make use of that data, for example, to estimate what would be the consumption of that particular consumer. Should we increase the mortgage rate? Should we allow that user, that resident, for example, to have access to higher mortgages? In terms of, for example, insurance companies, what kind of business model they can make out of that. So the data can be, that was initially used for the purpose of the utility company, now is used by another user, which is value co-creation. So I think Rafik has talked about the devices, so I will not actually emphasize on that here. But one important thing is that what we call multi-hopping or multi-hop communication, which is really very important because we talk about reducing the energy consumption of the devices, allowing the devices to communicate. But how it works simply works over short periods, over short distances, short periods of time, by optimizing also the sensing opportunities. So if you look here, for example, at the sensor node here, A, that tries to communicate its measured data to the sync node that collects the data, then it has to send its data over multi-hops. So this is what we call multi-hopping. And multi-hopping actually plays a very, very important role in terms of communication protocols and also in terms of security and intrusion into systems. So it's really very important to know. So here the device trade-offs, we have sensing, we have communication, processing, storage, intelligence, energy management, and so on. So we have a lot of things actually to take into account to optimize our devices. It's not only, of course, we have to come up with very sophisticated sensors, but also we need to communicate the data that is sensed and collected. So we can, for example, manage the mode of operation of the sensors. We can decide where to store the data. And also we can decide about the resources that we need for the data as well. It can be on the device, can be on the sync node, or the network, at the network edge, or in the cloud. So here, in terms of sensor technologies, researchers develop sensors, of course. They should be able also to integrate sensors and make them work collectively. They should also be able to provide the resources to the sensors to communicate in terms of, for example, spectrum, in terms of connectivity, in terms of being able to control these sensors remotely. Also contextual intelligence, which means that the sensors should know about their environment in order to be able to be better optimized. That's what we call cognition or awareness of the ecosystem in which the IoT is operating. So now, how IoT sensors and big data can play a role here. One important thing is that, as I mentioned, the data use is not restricted to the application for which it has been collected, but it can be used for other purposes and other end users. So this is the value co-creation that I mentioned. One example is, for example, a company in California. It was a startup. It was created from the need of parents who have their children using their cars. So these parents were concerned about the safety of their children. So they wanted to track in their children or their cars in real time. And this company, this is how they started. It was in a basement, and they used iPhones or cell phones at that time and equipped them with small GPS devices. So the initial goal of that company, or the initial purpose, is to track cars for these parents in need. However, the transportation ministry in California, they saw a good business on that. So they asked the company to provide other cars about this GPS tracking system. So now the purpose, instead of being the purpose of tracking children using the cars for their parents, now the purpose is to provide the data to the transportation ministry to manage and optimize the traffic and so on. And the data now, we can generalize this business case, for example, to utility companies that can use, for example, the data of location of cars, for example, to optimize the recharging system in case of electrical cars, for example, It can be used by the city planning services. It can be used by traffic management services. It can be used by insurance companies as well, healthcare services as well. So, of course, IoT applications, the speakers have talked about that, smart homes, energy, water, smart cities, healthcare, environment, natural resources, transportation, food and agriculture. Food traceability is a very important field as well. Retail and logistics, finance and insurance sectors, governance and policy making. Now, what we have today in terms of policy making and governance is that rules and laws and policies that come from the government to the citizens, and then they will wait probably 3 or 4 years till they receive feedback from people about whether this policy is making sense or not, and whether people are happy. And sometimes people go into strikes and have to demonstrate and show that and prove that this policy is not working or this policy is working. But with the Internet of Things, we can actually introduce and integrate IoT into the policy making cycle, into the governance cycle, so that policymakers, they can actually receive real-time information about the feedback about how this policy is affecting people or is helping people, or the opposite. For example, we can think, for example, of the speed limit in a highway. Okay, so with the Internet of Things, you can actually track exactly whether people are respecting that speed limit, that policy or not, whether people are happy of that or of it, whether it reduces accidents, and so on. So we can actually have a real-time feedback from people, and so that the policymakers, they can actually adjust their policy making. So the whole way of governance will completely change. So here, just a few words about M2M. What we have seen so far is mostly M2M, which means that we have a standalone application that sends data to an end user, and that end user, whether it's a utility or a city, will make use of that data. So this is what we call machine-to-machine communication. But the Internet of Things is really much wider than that. It's a wider concept. It integrates many applications altogether. It's not a standalone application, but many applications that are actually working together. So if you look in a smart city context, for example, you have data from the water distribution system, you have data about smart homes, pollution level in the city, and about the road traffic and so on. And this can be used by the smart grid, by the city, by the fire department, by hospitals, and so on. So I will actually here just an example in healthcare. If you consider, for example, stress disorder, what a classical doctor would focus, or a doctor with classical techniques would focus on, is probably the heart rate of the patient, the blood pressure, sleeping profile, use of medications. But with the Internet of Things, the doctor can actually integrate much more information that can add into the classical and basic information. It can be the living conditions of the patient. For example, if it has a smart home, doctor can receive information about the living conditions, the work condition. We can talk about smart companies, pollution level and noise in the city. It can add, it can be an important factor in the health condition of the patient. The public transportation system, how much the patient spends time in commuting and so on. And probably also some other information like virus propagation and so on. So this is the Internet of Things. It's not simply one specific application, but it's really an integration of many applications, many types of data altogether. And this is actually one of my projects that I'm planning to actually work on. It's called Smart Canada or Smart Country. So here actually Cisco has about 8 chairs in Canada in many universities, and the last one is in Carleton. So here the idea is really to develop IoT applications in many Canadian cities, starting from Halifax with the smart city, with smart cars, smart hospital, through the highways here, the 401 that goes through Ontario, so we'll have highway, intelligent portions of the highway through Ottawa, so with the smart hospital, smart airport, and so on, and all the way to Winnipeg and Edmonton. So here the idea is really to have smart collaborating hospitals, smart cities that collaborate together. We can talk also about security of the country, smart airports that collaborate together, and smart highways also that collaborate together. So we have this holistic view that the Internet of Things that can help, that can provide, and that can make a country like Canada, it's wide, but it can be smart, like a smart home. So it's really very, very, very also data intensive. Okay, so I think I will just conclude here. The IoT will include or will impact objects, individuals, and societies, and policymakers. The IoT will lead to major paradigm changes in the economy, environment, society, governance, and policy making. And of course, all aspects of the IoT system has to be considered, starting from the data level to the technology development, to data analytics, computing, business, and also the adoption of the technology, because it's very important to develop a very good technology, very sophisticated technology, but the adoption process is very important. The technology has to be adopted and has to be actually designed so that doctors, city managers, governments can adopt the technology, and also can be able also to be ready to make changes in their way of working and way of thinking about data and the Internet of Things. Thank you very much.
I'd like to thank our speakers, and now we'll open the floor for a few questions before the coffee break. So, questions? Yeah?
To all the panelists, and I'm just interested to know about your data analysis pipelines, in particular, what software packages or languages do you use in your data analysis? What do you find works particularly well for your use cases, and is there anything missing in terms of like what the packages have, or just in general? I really wish I could visualize data this way or analyze data this way, and I don't know how or can't. Thank you.
Well, I'll start with myself. I use SAS for pretty much all my statistical analysis. Now, I have the version that sits on my computer in my desk at the back of Herzberg that runs reasonably well. But when I get into some of the larger data sets at Stats Canada, I'll run the SAS off the server, because you can imagine with the 2 million people and then linked every year, like we get very large files with lots of variables. But I pretty much exclusively use SAS.
Yeah, actually, I use mostly very basic, classification tools for data analytics. However, the Internet of Things is now a vision. It's not there yet, and the amounts of data are really huge. What we have today are mostly standalone applications. We have image processing. We have like pulse data. It's for dedicated purposes. So most of the tools now are dedicated. But my personal expectation in the future is that to have multiple tools that work together, because the data is really huge and heterogeneous from different types with different kinds. So.
I study the tool makers, so my tools are a little bit different, but I would use qualitative analytical tools such as In Vivo. I'll use Mind Map to try and map things out a little bit. Because I tend to work graphically, I'll use whatever package I can get my hands on to look at things more graphically, and I'm starting to look more into how I can do some more intelligent and faster text mining, because the gray literature that I've accumulated from multiple organizations is really starting to accumulate. So I have to find a better way to sort it, and I certainly have to find a better way to analyze it.
I don't think so we can answer the question that you're asking. It really depends on the problem. And I use a lot of R for my analysis, data analysis, and we are teaching R in our data science program here. And R is really powerful in handling big, large amounts of data. But I guess I have an advantage here as well, that I usually craft my own scripts. So I write my own scripts because I have that background and I can code. But if I think for us, for example, running applications that can be challenging. So they have to be live, they have to be dynamic, and this would require different type of, it will require coding as well. So for the data analysis, I think R is quite powerful tool to do any kind of analysis. Yeah.
Thank you. Questions?
Yes, hello. I'm a student at Algonquin College, and I'm tending to focus on security and privacy in my studies. I'm wondering if you teach and focus on that as part of your programs, and also if you can discuss sort of the advantages and disadvantages of having open data. For example, I know Hydro Ottawa releases residents' electricity usage. One benefit is you can figure out what devices use what, but a negative aspect of that is someone can determine if you're not home and invade your privacy, or it can be used for like insurance companies to penalize people and stuff like that. So if you can discuss that, I'm especially interested to see if Carleton focuses on that as part of the studies. Thank you.
Okay. We have actually security courses. I think Jim can elaborate on that. Actually, this is a very interesting, very important area, because any device that you develop or any Internet of Things application, big data application, security is number one. So the end users will ask first about security. And this is a major threat, and it is being addressed, and it has to be addressed all the way. I think Jim can mention, talk about the courses or specific courses that we have.
Yeah, maybe I'll add as well, like that's a very important issue, and certainly it's covered from a technical perspective. There are courses in the School of Computer Science, courses in engineering that deal with security, but also there is the security from a policy perspective, how to deal with security on that aspect. And we actually do have a master's degree here called Masters in Infrastructure Protection and International Security that deals with some of those aspects. So maybe you want to elaborate a bit from a communications or journal?
Yes. From a communications perspective, we certainly do. So in critical data studies, this is one of the key things that we take a look at. In the School of Public Policy, also in the Faculty of Public Affairs, it's also something that we look at. So for instance, my alarm bell started to ring when we started to talk about value co-creation and insurance companies. Because for me, the last thing I want is my water consumption. Maybe I want to drive a little bit fast. Maybe I want to go to a neighborhood that's a little iffy. I want to have the option to opt out of the Internet of Things. I want the option to opt out of being monitored and surveyed. And I want the option as a society to make decisions as to whether or not where we go as a city, and whether or not as a city we wish to implement these techniques and technologies. And if so, how do we govern them as a city? Do we let the engineers govern, or do we govern? And what are the privacy by design implications? What are the social implications of deploying these kinds of technologies? So we certainly discuss a lot of those questions in communications and media studies. With regards to open data, there are multiple implications related to that as well. Generally, the open data that we're finding right now in most open data portals in cities and provinces and territories and in nations is pretty low-hanging fruit kind of data. Most of those data are anonymized. And so there aren't many issues. There are some issues where you might be able to do some co-matching of those data and uniquely identify people, but once we start getting into health, those data are generally not available. So there are certainly some growing questions and a lot of discussion about privacy with respect to open data as well. So we do have those conversations.
Thank you. Maybe one more question, and then we'll go to the coffee break.
Hi, my name is Mary O'Keefe. I'm with Health Canada, and building on this young man's very pertinent question, there were also a lot of alarm bells for me in that discussion about the Internet of Things. So there are we deal with within government huge conflicts between privacy and security, and much of our infrastructure at any level of government, think of the telecommunication system, for example, was developed without thinking about the risks of cybersecurity and hacking from people and governments who have very nefarious objectives. So we develop things in sort of a naive way, thinking, oh, isn't this wonderful to share everything? There are also enormous legal and ethical dilemmas about sharing data that was collected for a specific purpose. So there was no discussion really about permission-based, and the average citizen has no capacity to grasp what that means. So you see like a dilemma between Apple and Google on this issue of the FBI trying to get into those iPhones from the terrorists. So the FBI has finally figured out how to do that themselves, and they don't need Apple anymore. But, I mean, those are two very different business models. Apple charges for its products and does not trade in your data. Google gives you everything for free, Google Maps, Google Search, all kinds of things. But they're trading in your data all the time, and people don't really understand that. So I think there are incredible risks as well as incredible benefits. And I've been involved in developing a big data strategy for Health Canada. And it's just, you know, we're a regulatory agency. We gather huge amounts of confidential business information on, say, the pharmaceutical industry. And, you know, there are huge implications. It's very complex and needs a lot more study. And I would really encourage the university to delve more deeply into those conflicts between privacy and security. Be a huge benefit for government. Thank you.
Sure. Given that I work with health data as well, too. So, yeah, there are tremendous issues. When you think of even someone's 6-character postal code and getting their latitude and longitude and having access to information about their health status, there are huge ethical issues around that. Now, a lot of the data that we work with happen to be housed at Statistics Canada. So the only place we can go in and analyze those data is under the StatsCan roof. Some of the exposure surfaces, on the other hand, that are generated, you can download from various websites at Dalhousie. So those are more easily accessible. But tying the two becomes a challenge, and especially with REBs now. So one thing we'll often do is that we'll assign exposures to, say, our postal code data independently of the health data, and then we'll merge it back to the health data, and they'll create an analysis file that'll be stripped of all the personal identifiable information. So there are some things we can do, but I think there are still tremendous issues around it, especially once you have GPS monitors being brought into play too.
Yeah, like find my iPhone, for example, find my phone, or various other things. It's yeah.
I think one of the other important things is also the terms of use, and also, do you actually own the data from the device? So a lot of so for instance, you were talking about sleep apnea devices. Well, if you have a sleep apnea device, you actually don't own the data that is tracked. You have to go back to the company to get those data about you. So they know a lot about you, but you don't get to know a lot about yourself, and you don't get to know a lot about how you fit in to a broader picture. So there's certainly terms of use, there's privacy, there's access, there's shareability, and then the unintended use one. You know, we see this issue with credit scoring. You're using credit cards, and then suddenly you're realizing that you're part of a credit score. Then suddenly we're realizing that social media is being used to assess your credit score, and suddenly there's an awful lot of people know a lot about you, about something that you have no control over because it's not regulated by the state in an effective way, and it remains in the hands of the private sector. And I think the same goes true with procurement. So if a city procures sensors, what rights do they have over it? What rights do they have over the data? And how do they get to oversee the information that's coming in and out of the city?
And certainly we're seeing now the tip of the iceberg, because this is a very, very, very big issue, big data issue as well. Okay, so thank you very much. So now we have the coffee break, so we should come back here in 30 minutes. I guess coffee breaks are very important for socialization, so we'll come back here in 30 minutes. Thank you.
So we'll now pass over to the next session, and that's wherever our chair is, probably heading in. Over you.
Okay, well, thanks very much, John. So this session is going to be more focused now on government and private sector needs in data science and analytics. And so we have 4 presenters with us today. 2 of them are going to give presentations, but the last 2 are actually going to engage in a bit more of a fireside chat as a means of talking amongst themselves, but also engaging the audience in some of this discussion. So I'll bring them up one at a time in the order they're going to present. We have Dave Thomas, who is well known to many of us at Carleton and also in the local business community, who's the chief scientist at CSO at First Derivatives. And then we have John Milne. John Milne's the managing director of innovation at Invest Ottawa, and also well known to many people in the room, I think. And then we also have Stephen Normore, senior software engineer at Shopify. And Stephen is going to tell us a little bit about some of the work there. He's very active in some of their real-time analytics that are happening at Shopify. So an interesting topical point for us today, too. So if I can invite you up to the front, please, to seat.
Well, good morning. It's a great pleasure to be back at Carleton. Those of you who know, I'm a very scruffy ex-professor, still an adjunct at Carleton. It's a great privilege to be here. It's very good to me as a student and as a faculty member. I took the directions very explicitly when I got the email, so I'm going to talk about a much more mundane and uninteresting subject previous to Marie. However, I think they may come together at the end of my talk. So since everyone wants to do some data science, I thought, the best way to prepare for this was, of course, to do some research. So and for many people, Google's a mystery, so obviously it uses machine learning and all sorts of really fancy stuff. So clearly we can go out there and we can ask Google, what does industry think about, data science and analytics? And fortunately, one of the pages that comes up very early is this American commercial company. Of course, being a Canadian, we always have to do Google into the US first because that's where we'll find out what's really happening, right? Still a sad comment. And basically, this is apparently what industry wants because this company sells courses for lots of money. When I was a graduate student, there was something called the Masters of AI at Stanford, and it was called the Masters of Money. For many people, data science is the new Masters of Money because of the high pay scales that are quoted in the United States in particular. So in here we have a catalog of roles. I don't plan to take you through these. There's data scientists, there's a data analyst, there's a data architect, there's a data engineer, and you see they all contain things that probably most of the students in the room have and are studying, which are tools, practices, background, math and science and so on, all the things that you'd expect to have for people like this. Statisticians, good to know there's still statisticians around. I'll come back to that point. Database administrators, business analysts, they're still important too. They're the people that actually explain to the people who don't know, who are a data scientist but understand nothing about the domain, what's actually relevant. I'll come back to that point too. And of course, we have some sort of managers that have to deal with herding the cats that fly all these cool Hadoop machines and do all this machine learning and so on. And basically, it's a bit in my company, at least the part, not the part that I'm involved in, but does a lot of high performance analytics. And for years, it's been in the financial industry since they've needed high performance analytics. And there are people there called quants, or financial engineers, which is perhaps a euphemism. I'm not sure it's fair to engineering or finance. But basically, they spend, and often you'll go in and there's the traders, and they said, well, don't you have any quants? Because if you don't have quants, then you can't be a real investment house. So they take you into a room, there's a whole bunch of computers with 64 screens that people are looking at. They go, oh, okay, you guys must really know what to do with my money. I trust you. And if they don't like technology, then they take them to another room where there's people called chartists or technical chartists of the stock market, and they sort of have a Ouija board with a pen, and they show them those. And in both cases, they say, well, this company's clearly got all things covered. And if you haven't seen the latest movie, you should definitely see it. It actually feels much more like a documentary than a story. Now, for those of you that are going into data science, it may be a dream job, but you could find yourself that your main job is actually trying to collect the data in Africa or some other place, which actually probably is a much more significant thing to do than what you're going to do with your data science, just to put things in perspective. It's very important to know where the data comes from. More and more of this data is about individuals. And it's critically important that we be sensitive to that fact. Now, the dirty truth about data science, of course, is that 80% of the work is trying to get the data and then trying to clean it into a form so you can actually use it. Many people I know in data science actually said, how did you get the number so low? And then there's about 10% of the time where you get to the really exciting stuff that you were trained in, run your analytics, formulate a hypothesis, And then the next part is the other hard part is you've done this really, even something as simple as a regression is magic to many people. That's why they call it machine learning today, right? So in case they understand you're just doing a regression, we're not doing that. We're doing machine learning. We need to fuzzify it so we can charge more for it. But the last part is this critical part. How do you explain it to people that typically don't understand the material you're working with or the kind of analysis you're doing? How do you communicate that to executives or government leaders so that they can make actionable decisions? So those are the last two parts are the kind of real data science part, but most of the time we're spent doing horrible things that are basically ETL, blue-collar programming on dirty data. However, the real challenges, I think, are these. First one I'll call data literacy. It's being comfortable with measurement and statistics. Yes, of course, we teach some people in some schools statistics, but we don't do very much in our high schools. And we don't teach very much about measurement. Wonderful book called How to Measure Anything, Nate Silver's. If you've never read it, you should. Today, given the tools that are available, you have to be good to expert in terms of your computational literacy. You need to be able to fly a bunch of different programming languages, take a bunch of rocks and sticks and glue them together into what's called a data pipeline. If you're going to be with it in the future, you need to forget about object-oriented programming, all that bad stuff we did here at Carleton many years ago, because now it's functional programming. Changes the way you think. You have to deal with these complex pipelines, but more importantly, you have to deal with huge amounts of data. Soon you'll be able to put a petabyte on a USB stick. It's only 10 years out. Next year, you'll be able to put 10 terabytes on a USB stick. 10 terabytes, 20 compressed. You need to understand the semantics of data. It's really easy to do queries when you have 3 or 4 tables. When you have, 500 tables that are in a common data warehouse and you're going to do it, it's very easy to do semantic joins that are meaningless. Almost very few programs anywhere in North America teach people about data semantics. Most students, undergrad, who hear about ER models and database go, ugh. Right? Or else they teach you how to implement a database. But database design is a lost art. Understanding rich data semantics and how to do joins, and particularly fuzzy joins over complex data, is a very, very difficult problem. It leads us to make interpretations about data that's very important that could be wrong. Data semantics is very, very important. And so is metadata, which is data about that data. There's an urgent need for what I'll call query literacy, because in my viewpoint, the future of programming and the future of computation is writing queries. All new techniques, from building compilers and runtimes to analyzing networks to dealing with almost any aspect computing, are more and more increasingly expressed as queries, except we don't really know even how to express those queries in English or French, let alone how to express them in a computer language. Most people can't read SQL, as written. And these are for simple queries. You can pass around 20, 30 lines of SQL, and people will scratch their heads, what does it mean? Even more, you can say, okay, we've got all the data, what's the question? We don't talk about this. We don't teach people how to think about queries. This is really, really important. We will be able to query almost anything if we could write the query, but we can't. We need to learn. Diversity and depth. I mean, you don't solve problems like the Ebola crisis by sending a bunch of specialists someplace, right? There'll be a few specialists. You need the T-shaped people, right? We need those people who have depth and something and breadth. Today, the future of computing and technology is not the technology, it's what the technology can do when partnered with domain expertise. So it's very, very important to have specialists, but your success will be controlled very much by your generalists and by those who come from different backgrounds. So it's very important to have cross-functional collaborative teams which embrace diversity of thought and backgrounds. I can just remember a funny story sitting in the School of Computer Science just after the building was built. And Professor Atkinson there at the time, who was has a strong math background, and my background is, I'm very scruffy from engineering originally. And he was writing at the board, with another colleague, and they said, oh, we can't figure what this problem is. It just seems to be, look at this, it's, going, and they're writing these. They said, it seems like it's going sort of up and down. I said, it's a Fourier series. They went, oh my God, and they published 3 papers, and they wanted to put my name in. I said, no, I didn't really contribute. I just, from the world I'm from in engineering, I know a Fourier series when I see one. But they were combinatorics. Even in simple, fairly narrow domains, the fact that you mingle with people who think differently gives you great insights. And one of the privileges and pleasures that John Golak is here, who we worked together between computer science and engineering, and particularly mechanical engineering and so on. And a lot of students learned a lot more about problem solving from John than they ever did from me. The other issue is we really lack serious domain expertise. In the top of many corporations, I work globally with many large corporations, there really aren't many people who really know what the business does. It's really scary. You keep going, well, there must be a smart guy, take me to the next level, right? Well, taking to the next level, they often get dumber and dumber. They may be smart in general principles, but in terms of having a deep understanding or knowing what their business is and where it's going, there really is a real shortage. We really need problem solvers and communicators, and this again comes from a diversity and also comes from teaching people about synthesis. One of the things I always admired about the School of Architecture on this campus and design relative to other things is they spend a lot of time actually building things as opposed to analyzing them. In science and engineering, we spend a lot of time figuring out how to analyze things and taking them apart, but we don't spend nearly enough time building them and putting them together. So I think the ability to do synthesis and so on as part of a university program is really, really critical. And certainly co-op education contributes a lot to that, be able to be participating in a synthesis organization. Making decisions fast is very important. Making informed decisions fast, even more important. Dealing with those in uncertainty is a problem. We do not educate most of our children in uncertainty and dealing with uncertainty. We're very uncomfortable as humans with uncertainty. We need to feel a lot more comfortable with uncertainty so that we can deal with it. If you just look at instances of terrible things that happen and say, so what's the probability of that happening? And people go, well, it could happen any time. Well, it could, but there is a probability of that happening, but most people are not comfortable with those statistics. We need to improve visual literacy. We can do amazing things now with visually. I wish we could do more amazing things with sound because it's a resource that we could really use and doesn't suck up the bandwidth that we have. But our visual literacy, our ability to see things and communicate them visually is actually very weak. Doesn't everyone take a drawing course or do some art? Oh, perhaps you do at home. Yeah. Surely we don't have to put a course for ethics in our program. Can we leave that for the families at home and society and perhaps put in those kind of basic skills of art and music back into our program? You know, one of the best predictors for hiring that we use is if the students have music plus functional programming. The music's probably more important. The ability to communicate effectively to stakeholders. How much do we emphasize writing and communication? Well, a bit more in a graduate program because you have to write that thesis. But we don't have enough, critical thought, looking at papers and so on. The last thing, and I'll finish here, is we need usable tools. Basically, the tools today are really rocks and sticks. They're very primitive. They're very complicated to use. They use the word batch. The last time I used batch was when I had to use punch cards and wait for the results to come back. That's called Hadoop, maybe slightly faster by Spark, right? The world I live in, we live interactively in the data and need to make decisions in milliseconds or nanoseconds, or certainly within hours or days. Many companies that use large amounts of data actually run blind for periods of hours because they can't analyze their log files to figure out what's actually going on in their business. So they're actually running their business blind for periods of hours. The stock market crash basically was companies running blind for periods of months because they couldn't evaluate their CDOs. It was a lack of computational tractability as well as just crookedness. The complexity of the data technology is very high. Today there's a magic. Now that Google, of course, has their AlphaGo and has been successful at Go championships, everyone is convinced that we'll all be unemployed, which may be true or maybe not. We don't know. But somehow we're going to be overtaken by machine learning. We need to be very careful of magic. I was around in the early days of AI and watched it come and go. Machine learning is very useful, very important. It's a very useful tool, but we must master it, not be hostage to it. We need to democratize access to data so that people who need it can easily get at without having to bow at the high priest, right? Basically going and beg, could you please run this analysis for me? I'm sorry, I can't program in Java, Python, and R simultaneously at the same time like you. And by the way, you gave me the wrong answers the last time. Because it's just too hard. We need to be able to develop pervasive respect and tooling and technology that supports privacy and access to personal data. Many years in Canada, we should get someone to talk at Census Canada, very much restricted the amount of sample size that you could get back in a query so that you could not target individuals in this country from census data. I believe we need to apply the same things. The reality is that in the world today, we'll be forced to actually look at data even when we don't want to. It's a very difficult challenge. But if we control how much data they can look at, how long they have that data, who has it, and record and track that, then at least we can have some way to be credible and to be able to ensure people in our country that they can instill trust in them. And we need tools that can be accountable for their own behavior. We're going to use machine learning or sophisticated analytics or even SQL queries. We should be able to have a tool that you could give an SQL query and actually could tell you in English what the query means. There's a great PhD problem. Yeah. And after that, you can try and do Hive and another mess, but that'll be 5 PhDs. Thank you very much.
Well, thanks, Dave. And with that very provocative talk, I'm going to pass it over for a slightly different format now to John Milne and Stephen Normore, who are going to engage in a little bit of a chat around maybe the industry perspective. And John actually brings an interesting perspective to that question too, because in some ways working at Invest Ottawa, you're a mix of government, academic, industry, social, the whole range. So I'll turn it over to both of you, and we'll see where this takes us. Hopefully you don't need a moderator. Okay.
Is this on? All right, here we go. So we are between you and free lunch. So we're going to just change up the pace a little bit. So I'm going to ask Stephen a couple questions, and then we're going to open up to you guys, because I'm sure you're all sitting there dying to ask something, because you guys have been listening for the last couple hours. So a very simple one, Stephen. Did Shopify start off as a data company?
Did we start off as a data company? In some ways, yes, but we didn't start off as a mature data company. We went through the classic evolution of our data platform, our data organization, making a lot of mistakes. Throughout the years, we've evolved into a much more mature situation where we focus much more on context and less on the data. Something I wanted to bring up was contextless data is very much useless in a lot of scenarios. The SQL query to English translation is an example of that. Without context, what does the English translation mean? You always want to focus on the problems that you're solving, basically.
So a lot of decisions at Shopify have been data-driven, right? Both internally and externally. So why don't you describe some of the data that you collect just on employees as an example on how culture is created at Shopify?
Right, great question. So we definitely collect data on employees. We collect data on candidates. We collect data on potential candidates, potential employees. One interesting thing that we collect is kind of like the Enneagram personality types of every employee. That plays very much into our team structures, our managers, our leaderships. Our leadership is very well versed in those concepts, and we build teams, our optimal teams based on optimal personality aggregates.
All right, so now you've just hired somebody to kind of take over the data team at Shopify, someone very senior from Netflix. By the way, speaking May 5th at Accelerate OTT, so I'll put my little plug in there, Malcom, on some data. How has he structured the team now that he's come in and kind of looked at where you've gone in now to your maturity model?
So it goes back to what problems you're solving, or the purpose again. One of the first things David did when he joined Shopify was define two sub-organizations within the data and analytics organization. First, Shopify has merchants or customers who have customers. So we also are responsible for helping our customers solve their problems and basically provide decision support for our customers. So the structure that David broke it into was Shopify optimizations and merchant optimizations. Those are two teams with a purpose by name. That's intentional, and Shopify optimizations obviously being internal optimizations or internal data needs, and merchant optimizations being merchant-facing data needs.
So I can't remember the number, 150,000 stores now, 250? Wow, I got to keep up. So 250,000 stores, billions of dollars in transactions. You have customers who have customers. You've got an app platform. That's a lot of data. So you got that network effect going on. How do you deal with privacy now? Because of so much data you know. How do you kind of protect your merchants, the customers, yourself? How does the privacy now play in a network effect?
Great. So one of the first things we did was hire some very smart people to make sure we were doing the right thing. And so from just a PII, personally identifiable information standpoint, we scrub a lot of data at the source before it ever leaves our core systems. We expire data. We're set up to basically nuke any customer's data if it's been requested. standard things like that. From a network perspective, network effects perspective, which essentially is providing value by networking, networking the data rather than just having using the single data set of a single customer, for example. So the important thing there is to make sure you aggregate well enough. You're not presenting data that's from a small niche, so the aggregate would be identifiable, things like that.
So what project are you currently working on your team?
So I lead the merchant analytics engineering group at Shopify. So my focus on a daily basis is very much the merchant optimizations side of the organization. And one of the interesting topics that we're focused a lot on is network effects, and how do we get merchants to their first sale as quickly as we can. We've seen in our data that merchants that can get to their first sale quickly are more likely to be successful. So some ways we're doing that is very much around recommendation engines in many different ways: app recommendations, theme recommendations, even just action recommendations. How do I set up my store? What's the optimal way to set up my store and get to the first sale?
And so how much does the customer see versus what you have internally? Like what is the end user experience looks like? Are they querying the data? Are they going down into SQL, or are you providing a kind of an environment where they don't actually have to know what's the secret sauce in the back end?
We mostly provide an environment where they don't have to know. We do have reporting UIs for merchants. In general, though, we're kind of giving them data without context again. You say, here's your data, figure it out. That's not the optimal way of doing that. What we like to do is, so we do have a query language called Shopify QL that we provide to app developers and higher-end merchants. And that sounds flexible, but it's really not. It's much more purpose-built for specific verticals of your business. So marketing, engagement, traffic, sales, finance. So from the merchant perspective, ideally we want to give them data that will answer specific high-value questions and not just give them the flexibility to kind of hang themselves.
So we mentioned Hadoop and Spark, and I think you guys are on Spark now more. What other kind of tools is Shopify using that students need to kind of learn and understand to kind of work on your team?
So we're definitely a Hadoop and Spark shop. Our data platform is built on Hadoop, Spark with PySpark on top of that. We have a framework, ETL framework within that called Starscream. It's basically written in Python. We allow analysts to write R on top of that as well. In addition to that, one of the big things coming up is very much stream processing and real-time analytics. It's an extremely new field. It's obviously been around for a decade, but still, it's so immature and so difficult to use. Usability is so low. But at the same time, it's all about purpose and context. So I wouldn't say that in every case you want stream process, real-time analytics. An example of that would be I'm a merchant. I'm optimizing for purchasing from my suppliers, so I'm doing supplier analysis. I don't have to do that in real time. I do that once a quarter maybe, so I don't need that data in real time. So it's very much around data literacy is a big part of that. Understanding data, understanding the context, the importance of solving problems with data and not just having data.
All right, let's open up to the floor for questions. So I think there's 2 mics here, or if you just want to shout out, but it's always hard to get the first one, so someone's probably itching but not wanting to put their hand up. So, someone? Oh, here we go. That's all right.
So I'll start with one for you to prompt things.
Sure.
So you have a perspective on the whole sector in Ottawa.
Yeah.
Using it as an example, right from the very big, we have IBM with the Cognos legacy, down to the group of small, medium companies that Invest Ottawa spends a lot of time supporting. In terms of the biggest need you see in terms of Ottawa really being able to seize leadership right across that whole spectrum in data science analytics and the technologies that can emerge out of that, what do you see as the biggest gap or gaps?
The quick response I go right into is actually adoption of tools. So if you go down the valley and stuff, there are literally hundreds of companies being built on IBM Watson and other people's platforms. You take Uber, it's a no-stack technology. You know, the most most valued company in the world has very little tech itself. And so what we're seeing is the adoption of these new tools like Hadoop. There must have been about 12 dozen companies that are valued over $100 million each just around when that new technology came out. And so what's happening is that early adopters are finding really interesting niche problems and contexts to solve very quickly, and then they're getting bought out. And we don't see that as much in Ottawa anymore. We used to have kind of the advantage around Cognos and a few of the other tools, but we've seen a lot less of some of the emerging stuff. So if I take Hadoop, for example, we were a very late adopter to that market. I have seen very few IBM Watson analytic AI type startups being performed. And so I think there's an opportunity to take these interesting industry problems and quickly adapting with technology.
Okay, great. So questions from the floor.
More important.
Yeah, if there's a pause while people are reflecting, then certainly, Dave, if you want to chime in on something there too. Yeah.
I think one of the challenges is if you always play Me Too for California, you'll be on top of Hadoop stack, but it won't matter. Basically, you know, sometimes if you want to do things, you have to do things differently. Streaming high performance has been running in hedge funds for 30 years. Column stores existed in the late 60s in the financial markets. The whole vocabulary of topics and microservices comes from what hedge funds have been doing for 20, 30 years. It's just been captured by California and respun. But the problem is sitting on top of a Java architecture is fundamentally limiting in terms of performance. And even Spark will probably succeed if they can get Hive and it compiles directly to LLVM to bypass the Java stack. So there are lots of opportunities. The problem is if you're going to always consume whatever, even Hadoop and the follow-ons, which still have terrible performance, were mere copies of what Google did in C++ many years before. And when Google writes the paper, they've already discarded the technology. So when you're running with Hadoop and Spark, you're basically running on technology that Google discarded many, many years ago. Now, it's fine for industrial use if you've got enough computers and so on. Shopify does. But many people that need to do analytics need to do it a lot faster and a lot lower price point than Shopify does. The web allows certain things in economies of scale, and with Netflix and so on. But Netflix is a huge, huge expensive business to run. That's fine as long as no one optimizes that business. But you know, can they afford to consume 30% of Amazon's infrastructure forever if you get a competitor? So I think there are other opportunities there that you look otherwise. And if you come up with clever algorithms, and particularly if you tackle special domains such as Frank Dana's work, for instance, in biology and so on, I think there's a lot of really interesting opportunities. So open source is great. It's good to have free software, but there's lots of opportunities, and you can get stuck being the maintenance guy in open source. The bad news with open source is that somebody always has to maintain it, and no one pays you for the product, which means your valuation as a business is always lower.
I just wanted to mention too that there are big data as a service is a thing that is emerging right now and has been for a few years. So you want to kind of stand on the shoulders of those giants rather than building your own. Ideally, QOBull, there are a bunch of big data as a service companies out there that if you are starting a startup or if you are doing analysis on large data sets, don't build your own Hadoop cluster, please. Also, one thing that's really obvious that's happening is that people are using Hadoop and these large big data solutions for small data. Our laptops are very fast. You can basically do a lot of the work on that. So try and keep it simple to start.
Nowadays. Can you hear me? Yep. So Rob McClellan from StatCan, and I'm involved in the enterprise architecture program there, so trying to really bridge the business world of statistics and the actual technology. I guess a couple of key things here. I've had a couple of different careers now in my time, and how do we break down these barriers, right? I see people solving the same problems at an abstract level. The patterns are all very similar. You know, if you've got a solid grounding in graph theory, if you've got a whole pile of other kinds of techniques, and yet I see that because they're actually being carried out in different domains, different disciplines, they could be science, engineering, they could even be arts. I don't see an awful lot of crosstalk going on there, so there's a lot of missed opportunities. I think the second thing is I'm old enough to remember when handheld calculators were really novel. And so 10 digits of accuracy clearly had to be better than 1. So to the point of relevance of the result of the analysis, saw a great deck the other day from somebody at Eurostat around correlating the price of butter in Bangladesh with something else big in the financial world. Sure, it looked like there was a correlation. There actually wasn't, but you know the shape of the curve looked the same, right? So I guess really, how do we give people a solid grounding in critical thought? How do we break down the traditional barriers, particularly in government, where you have this bimodal world, right? You've got the people that are the domain people, you've got the IT people that are supposed to take orders. That's a really outdated model that just will not work as we go forward. So there's a couple of questions in there. I'm just interested in your thoughts. And the final one would be, how do we do social good with this, coming back to the original talk, right? So I think that there's some really compelling things. I've done work at another university with their innovation program. I'm really impressed in young students by their sort of corporate, their social responsibility interests. How do we actually amplify their efforts by taking advantage of what's in front of us? Let's take one of those.
The last one's easy, I think, or easier. I think clearly, you know, relative to the United States, the amount of data that the government releases publicly is actually quite small. So clearly, you know, sort of, you know, democratizing access to the public data in ways that are safe, which is the challenge, is clearly the first part. I think Tina's here. I think she's involved with, you know, there are lots and lots of people that are involved with hacks of human kindness and various things like this, where people are actually quite willing to put their time in to try and do this. In many cases, there's a lot of difficulty getting access to the data sets. So I think getting access to data is the easy one. I think we're just way too, the deeper problem about the critical, I think we're just way too siloed. Right. I mean, basically, you know, when I started in computer science here, I think we only had one honest computer scientist. Right. And, you know, the rest were from engineering and physics and math. And you know, Frank Dopacker was a philosopher who couldn't work skiing anymore, so his wife made him get a real job. You know, and you know, but we had that eclectic mix. And I think we need to find some way to create, like the close encounters I had with John Goldak and people in psychology, late Dick Dillon, they really created these kind of multicultural perspectives. And I think, you know, engaging across disciplines and so on, and hiring teams, I think as an employer, trying to hire a more diverse team instead of just hiring a CS student, you know, mix them with some other people. I know we have a real problem with visual thinking, real problem with statistics with regards to the skills in computer science students relative to others. So mixing in a math grad or so on, hire a team instead of doing it. I think that creates another opportunity.
I think you also run into that with lack of data literacy. So you're going to solve the same problem if you don't know that it's been solved already.
Yeah, so to build on that comment about the social innovation, step one, of course, is open up the data. But actually, step two is to standardize that data sets. What we're finding is that almost every city has a pothole app. And the amount of effort to create these pothole apps are absolutely enormous. Yet it's the same problem, but they all had to be customized for the data set. So if we can start to standardize these data sets for big projects around the world, we can actually start to have a global innovation around social good versus compartmentalized. And that's the same issue with education. It's the same issue with startups. To solve the cross-pollination, the best teams are designed now without silos. So even the data science team here actually is one of the first units that wants to go across the university versus living in one department. And so university is actually the first place that needs to realize innovation comes from cross-pollination between the different fields. And taking someone from who's not from your field tends to actually solve your problems better, right? So, the person that's going to solve the next biology break is not going to come from biology. And that's what I think is going to happen when we start to break down these silos.
Too often what you see in startups too is when they talk about cross-functional teams, they have designers, engineers, UX people, but they don't include data in that. That's one super important thing that we learned in the last couple of years was that data essentially needs to be at the table with the rest of the team.
Well, my question is for Anne-Marie, so I see you have the mic. Thank you, Dave. So, the major outbreaks that occurred, a couple of years ago in Sierra Leone, Liberia, and where else was it? Guinea. You indicated that data must have been collected during these. First of all, it was heterogeneous because there were 3 different, probably more, regimes that were not particularly interested but had to collect it. So that's the first challenge. Is there any attempts to harmonize that? And if so, could that have been used in the most recent Easter outbreak to do some predictive analytics vis-a-vis the spread or the containment of so? You must have thought of that, and it must be very frustrating.
Well, yes. So the 3 countries, and I'm not as familiar with Guinea and Liberia, but they used, first of all, Liberia and Sierra Leone, I think, are English colonies. Guinea is a French colony. And I think their way they react to their governments, the intervention of their governments were different. And so in Liberia and Sierra Leone, and mostly in Sierra Leone, when it came time to quarantine people, they were able to use the army. In Guinea, they refused to use the army because they were afraid that there would be a revolution. When the head of the response went to Liberia and he actually talked to people who were in quarantine, when he came back and reported to us, he said, "You should have seen their eyes. They were so sad because they were quarantined by the army." Here in Guinea, we decided to do it in a softer way and not quarantine people. So it's very dependent, I think, on the culture, the approach to the containment of the outbreak, and then the reaction of the people towards the outbreak and preventing it. I think also important is the literacy level of the country. Initially, we had, CDC had people in charge of communication who did not speak French, so they had a translator. So you know how things get lost in translation. So, pardon? Yes, exactly. Yes, exactly. So, so the challenges that we experience in collecting the data were the same in containing the outbreak. They had a repercussion, like they weren't independent from each other. I can't really, we had a presentation from Liberia when they were able to contain their epidemic, and they had a different approach, but I would say that the population's reaction to the disease was different in Guinea. And that's why it took so long. It started in Guinea, the outbreak, and just right to the next to the border of Sierra Leone and Liberia, and there are no borders for them. They just cross. So they live in Guinea, but their farmland is in Liberia or Sierra Leone, and so they went back and forth, and the rest is history.
Before lunch, yeah.
Hi, I'm Fazan from IBM. So I was listening to Dave, and I completely agree with you that 80% of and data engineers' time is spent in cleaning the data, and the analytics part really doesn't take, I mean, it does take a lot, but once you have the data in the format you want, it's a smooth ride from there on. So what my question basically is that we all know that a certain data set, many data sets, they always have outliers or noise in them. So when you're deciding to take decisions based on data, do you keep a gap, or do you take consideration that noise, or do you fully believe in the data and make business decisions 100% based on that? Or do you sometimes think, no, I'm not totally going to go with this because there might be some outliers in that, and I can't risk everything just on what the data is telling me. So where does that fine line between totally blind faith in data and, taking it with a grain of salt?
So I think the answer is context again. The answer basically is yes, we do both. And it depends on the context. If the source of the data is a good piece of context, if it's not reliable, if it's not trustworthy, or if it's been shown over time not to be reliable or trustworthy, then absolutely you're gonna remove outliers from that.
Missing data and data that's out of band and so on. I mean, if you're dealing with IoT data, the bad news about sensors is they're actually in the real world, so they fail all the time. So it's really bad for computer scientists, right? Basically, this stuff just doesn't work. So you have to be able to deal with that, and part of your data transformation process, or your ETL pipeline, if you want to call it that, is dealing with missing data. The other thing is we use, there are lots of techniques. We use Dempster-Schafer, which is a technique for reasoning about data with uncertainty in it. So you actually characterize the uncertainty, and that gives you a high-performance technique for actually doing computations on data with uncertainty. So there are techniques for doing that, and if you're really, but you need to characterize your data. You need to understand that that it's a sample from a given population, and be able to characterize it and use the appropriate techniques for doing it. It's very important to be able to carry that uncertainty through. What a lot of people do is say, oh, well, this data is missing, so I'll just toss all those records, or I'll just fill them in with an average or something like that. And that's just going to ruin your data set and your analysis.
There'll be a chance to chat over lunch and afterwards. So join me, please, in thanking all the speakers again.